Okay. Uh,
Guys, do you know if this is going to continue in the second hour or whether it's going to repeat?
Repeat.
Repeat.
Yeah.
Working.
So I don't need to record now until we start the. So
now it's working. Okay.
but it hasn't started recording. So before.
The mic is working.
Yeah, it's
Is this
working.
one? Okay.
Yes.
Okay, perfect. Okay, if you need something else, this one. Okay.
Okay.
This meeting is being live streamed.
Yeah.
Are we live streaming them or not?
Yeah.
Right, so that's me. How to secure a database. Yes, that's that. That's that. Looks good to me.
Yeah. Well, when you do your first presentation, were you from nervous?
Yes and no. I do a lot of presentations, but I always feel slightly nervous when I do it somewhere new in front of an audience I don't know.
I haven't given a presentation in front of a group of people in conference meeting. I can't imagine.
It's practice. I mean, the thing is, if you enjoy your material and you enjoy talking to people about your material, then you're interesting and people love you. And if you have a fun presentation with it, then it's great.
Yeah.
But to be honest, when I was at university, I would hate doing presentations. Oh, we have an attendee! Hurrah! Congratulations on the first one. Nice to meet you.
Well, nice to meet you too. I guess I'm one of the, so I work at the intersection of compilers and databases,
Funky.
and I'm guessing there are not many people like that.
No, you're the first one I've ever met. Well done.
Nice.
So I'm the person. I'm also in this.
You also work in compilers and databases?
Not in this area.
That's programification, apparently.
Yeah.
Programification, I've never heard of that.
Programification.
Yeah, isn't that cool? I think you should be talking, not me.
Yeah.
Looks like you're getting a personal touch here.
No, I think people show up late anyway.
Okay. Well, you're a private lecture, I mean, you're doing well on that. You get the entire floor with Q&A.
So I think I saw in the program that you have no affiliation. I don't like. I think it said none. No.
I was not entirely sure what affiliation meant.
Okay.
Chaotic good, maybe.
Are you like you work at a company or are you
Yes.
a professor?
I work for a company called TI Tokyo.
Oh, okay, that's cool. And what do you folks do?
Well, I'll be explaining in a minute, but essentially OpenReact is one of the biggest things we do.
Oh, no, you did the port?
What?
Like from React?
To OpenReact, yes. There was our company, the NHS from the UK, and a Fortune 500 company who doesn't want to share their name. And the three of us came together under the Erlang Ecosystems Foundation to build OpenReact.
That's very cool.
So version 3.2.6 was released yesterday, unofficially, and we're currently building packages which will be released as soon as they're made available.
That's nice.
So yes, if you have any questions about OpenReact, I'm probably the best person to talk to in Singapore at the moment.
Well, that's cool. Yeah, as a matter of fact, I do. I mean, what? So I'm not very familiar with React and OpenReact. Does it have? So, what are the language interfaces, or let's say just the languages that one can interface with OpenReact?
Name a language.
Like SQL?
Done. SQL done.
Okay,
SQL is the only one you can't do, because it's SQL, and this is a NoSQL database.
okay, okay. I see. So Python, for example.
Yep, so we, the basic interfaces for React, we have a protocol buffers interface, and we have a HTTP API. And you
Okay.
can talk to it using either one.
I see.
So you can either do like I do, where I write a custom client that talks to whichever interface, depending on whatever code I'm writing. Or you can use one of the pre-packaged clients. So there's a Python client, there's a C client, there's a VB client, think of a language that's probably a client for it.
Okay.
Ruby client, I could go on, Golang, all kinds of weird, wonderful stuff.
Right. But Open React doesn't execute any languages in it, right?
That's a very loaded question. At the moment, you can write MapReduce queries in a mixture of Erlang and JavaScript, which will execute on the server. However, if you do that in production, I may have to shoot you. But theoretically, yes, you could do it. And if it's a ridiculously simple one, yes, go for it. If it's something as simple, if A then B, yeah, go for it, why not? But one of the things we had with one of our clients before is they decided their application team was useless and couldn't decide between stuff. So what the guy who ran the database did was he wrote this huge set of queries within Open React. So when the application gave it the wrong piece of data, they would then take that query, intercept the query, say, actually, you're not that, you're this, and then redefine the query and send it back into React.
Oh.
And they always wondered why React wasn't processing it. It was only doing 10 million data points a day. Why was it running the CPU so much? And it's not because React's working hard, no, it's because it's going through this amazing amount of code. We're not talking a few, we're talking about 400-500K of code here. So you're not meant to run your application in your database.
I see. Yeah. Okay.
So yes, you can do it, but you can shoot yourself in the foot.
So basically I'm asking, so for example, in say, I guess, I don't know, like Postgres or Spark, for example, one reason to write your UDF there is to be executed closer to the data. So instead of having, for example, things that get transferred from the database to the client and then you process it, the processing happens, for example, within Postgres, like
I think one of the biggest differences, and people often don't understand this, is that Postgres is great. You chuck your query in, it does a whole bunch of stuff for you and chunks the results in one big group to you. Open React does one query and gets one result, and it's blindingly fast. Open React processes in parallel.
Okay.
So if you send me 10 million queries, I'll give you 10 million results.
Right.
And as they're in parallel, they all hit your box at roughly the same time. Therefore, we query faster than Postgres does.
I see. So compared to say something like Spark, which also would process things in parallel.
Yes, there's actually a Spark plugin for React. It's out of date, but it does exist. We also have a Redis plugin as well for people who like to go that way to make compatibility. That's also out of date, but it does exist.
Oh, I need to look more into Open React. Yeah.
But yeah, one of the biggest differences with Postgres is everything is generally a relational database.
Right.
Whereas React is non-relational at all.
Yeah.
So what you have to do is, in something like Postgres, you may search where, I don't know, username equals a star, because you want to find everybody whose username has an A in it. Don't do that in React. That's a very, very bad idea.
Yeah.
And that's the one query you can't do in React. So what you would have to do in React is you store your data as you want to query it.
I see.
In Postgres, you make beautiful logical tables like you would in Excel, but just lots of them.
Yeah.
In React, what you do is you actually have to think, well, if I'm going to query this, so I'll do a query of, for example, username is my bucket name. So it's called buckets and keys, by the way. So bucket name would be username, and then key would be user.
Okay.
First name, user, last name, password, hash. So you
I
actually,
see.
and then you come in. So if you want the user data, then you'd actually make 3 queries. You query first name, last name, and password hash. And because you already know the username, that's the bucket name. So your first query is, can you get this data to React? And if you get a no found, you know the user doesn't exist.
I see. And it can support nested data, or is
Metadata?
nested?
Nested data. Yes, you can do all kinds of things. For example, you can encode a JSON blob. You can encode a binary. So yes, you can actually say, just get me all the data from user A, and then it will just return 1 JSON blob or 1 string to binary. And then you send that back to the client, and then you decrypt it in the client or analyze your JSON and pull out whatever you want from it. But you can stick anything in. So for example, you could have their avatar as a JPEG in there as well. And it's just, user picture, and then here's the JPEG.
That's nice. All right, that's cool. Well, thank you very much. Yeah,
You're
for all this
welcome.
information. I really should look more into it. Yeah. It's very different from the, I guess, the conceptual. I've had some experience with NoSQL databases, a little bit, DynamoDB, and I mean and then the other one that I can't remember now, but not so much. Yeah, really true. And definitely they were not distributed. No, Dynamo is,
yes.
Dynamo is, but it was very different in the sense that, so the way I was using it was as a service in Amazon, so it was a very different way of working with it than, say, the way you would work with Spark or Postgres.
Yes, I mean, that's one of the interesting things is people generally prefer that Dynamo because it's popular and it's well advertised. Thing is though, OpenReact works on commodity hardware as well. For example, I run a cluster on Raspberry Pis at home that does all my crypto taxes. So Japanese law, you have to report every single transaction at the Japanese yen version of it.
Oh.
So I actually record all my transactions. I record the exchange rate at every single point in time, both between the crypto and USTD, and then I do USTD to JPY. And combine the whole thing and have an application where I just fill in a list of my transactions and it reports it all back with the right numbers from the Japanese tax office. It runs on Raspberry Pis, but it's React. And the thing is though, apart from when it has to reach out and grab the newest transaction data, other than that, the entire thing runs offline. You can't run Dynamo offline. If you lose the internet, your entire system goes down. You can't run Dynamo in an air-gapped environment if your thing is busy. Sorry, if your thing's really secure, because it's a cloud service. Whereas this one here,
I see what you're saying. Yeah, you can't really put it in a box.
Yeah, well, as it looks like it may just be the two of you, I might as well do that. If you'd like to ask me any questions in future, here you go, that's me.
Thank you very much.
I give one to you as well.
Thank you.
There you go. はい、リベイラリーサーチをよろしくお願いします。ありがとうございます。
We'll start.
I think we should start it. It looks like you've got a private seminar. Congratulations.
Then we start the code.
Yep.
And let me check the. Yeah.
Good. Right. So, hello everybody. Nice to be here. Yes, so my name is Nicholas Adams. I've been sent here today by TO Tokyo, so I should probably say thank you to them. We have our excellent student assistant here, Yuyan, who's going to help us out with all the recordings. And I'll be talking about how to secure a distributed database such as OpenReact using open source tools. So without further ado, let's make a start. In today's session, we shall be talking about an introduction to TO Tokyo. Don't worry, there's a reason behind this other than just blowing our own trumpet. By the way, this is our company character though, Chio-chan. She's everywhere because she's cute. We're a Japanese company, we have to have a mascot, I'm sorry. So she's our company mascot. So yes, so anyway, we'll go on. We'll talk about what is OpenReact and when you should use it. Why is it insecure out of the box? There is a reason. Why that's still enough, not enough to secure it, which we'll cover when we get there. What else can we do? And we'll wrap the whole thing up with Q&A at the end. So an introduction to TO Tokyo. Yes, why am I here? Why am I talking to you? Well, first of all, our company was originally called the Training Institute of Tokyo because we trained people. Yes, we're actually trainers. We do this for a job. Unfortunately, people generally say, we like your training a lot, but it's much faster if you just do the work for us instead of training our staff, because our freshly trained staff are not that fast. So we segued into support and consulting, as you always do in things like this. So that's now our main bread and butter, is support and consulting. So we supported REAC, the open source, well, back then it was freemium, I want to say. There was an open source version which had a certain set of features, and then there was a premium version which had extra features. And of course, the premium one was paid. And this was run by a company called Basho back at the time. So 8 years ago, Basho contacted us and said, we want to increase our technical support presence in Asia. We need engineers who speak English, Japanese, and know REAC. And we said, what's REAC? They said, never mind, you speak English, Japanese, and you have sysadmin skills, that's good enough. And that's how we started. So yes, we supported REAC for over 8 years. Basho sadly went bankrupt in 2017. There was a completely botched buyout by the venture capitalists. And yeah, Basho died, which kind of sucked. But we didn't die because we were outsourced to, we were the APAC support. So what we did was, we hired some of their US engineers, we hired some of the European engineers, and we said, we're open for business. And everybody around the world who was still using React went, great, we don't have to change. Except for a few very short-sighted large companies who said, well, Basho's gone away, so it's going to fold. No, we're still here, guys. Just the world press seems to say no. So React did not die in 2017. React was actually bought, well, the IP was bought by a UK company called Bet365. Anybody heard of them?
The betting company?
Yes. Yeah, world's largest online betting company.
Yeah.
So they bought all the IP and they open sourced the IP, but wanted to run the project by themselves, mostly. They did allow one other person in as an external admin. And, you know, we kind of got on together and it kind of worked for a while, but eventually we thought the community wants to have their own voice of where we're going. So we forked everything off and we co-founded OpenReact with a National Health Service and a Fortune 500 company in 2014. And I actually got to announce the launch of this last year at a conference in Europe, which is cool.
So that's very new. So what is the, well, of OpenReact, but also what you forked, what is the license, roughly?
Patch 2, everything is free.
Really?
Yes,
Oh, wow.
so wild. Copy, paste, have one. Which is awesome. Everything in the world is free. Well, almost. If you want our support, you have to pay for it, sorry. But if you want general Q&A and stuff like that, check out the community, as that does have free Q&A in it. Hello. Right, so continuing, yes. So of course we co-founded the project, and as such we contribute to the OpenReact project as well. So recent one we talked about updates to the CRDTs, allowing, well, let's not go into category here now. Just it's a cool feature in React and we're looking to renew it to make it even better. Right, so going on. So what is OpenReact? Well, it seems people know about it, but for everybody who's watching, they probably want to know. So I go on, what is a distributed system? I should probably actually ask you though. So what is a distributed system? Anybody? Audience participation is awesome. Yes, go for it.
Different systems work together.
Nice. I wonder what gave you that idea. Yes. Oh, that's why I can't see my slides. I've got a little box over the top of them. Okay, so that is really hard to see. Yes, so runs on multiple machines simultaneously. Data is shared between the machines, and they commonly store multiple copies of data. They usually have some ability to scale. I'm not just reading my slides, I do actually think about things. And of course, yes, well, I'm going to read this one now. They have ability to process vast quantities of data. And to give you an example of this, one of our customers way back in 2017, at that point in time, they had over 14 petabytes of data in their React database. Yeah, 14 petabytes, 2017. That's quite a lot. And that's the kind of throughput we see in these things. I mean, Bet365, they process more transactions in React on the average Saturday afternoon than Amazon process in their entire Prime week. You know, that's the kind of data you can chunk through this thing. It is impressive. And of course, most people haven't heard of it, which is amazing, as it does all this awesome stuff. So yes, but of course, when you have incremental power like this, things will go wrong. So what can go wrong? Well, conflicting writes. Let's say if you're processing that ridiculous amount of data, and then two different writes saying different things come in at the same time, you can potentially run into issues of, well, which one's correct? Things out of sequence, if you're writing two long lists and then, you know, the first 10 values are equal, the 11th value is different, but the remaining 400 values are equal. What do I do here? Time for CRDTs or application level complex I forgot the word. Resolution, there we go. Yes, network partitions, another one. So let's say we've got a React cluster that has lots of nodes. Pretend these three objects are your React cluster. You should never use three in production, but I can only carry three at the same time. Let's pretend there are at least 5 here. So let's say the network splits and we end up with, pretend this is 2, and pretend this is 3. We have then this one here can still work, and this one here can still work. And if you have different writes to different ones, when the network becomes 1 again,
It broke.
or isn't it? And that's another one of the potential things with conflict resolution that you need to look at carefully with in React. How you set it up so you can actually have that work or not work accordingly. What else do you need to play with? Yes, performance spikes. One of the classic ones. Nothing happens, nothing happens, nothing happens. We are open for business. And then everything falls over. And that's again something that React is not particularly happy about. For example, if I was running OpenReact on my system, you really want to just run OpenReact on the box. I would not, for example, run OpenReact and Apache on the same box, because Apache's traffic is like this all the time, whereas OpenReact generally runs like that and doesn't compete very well for system resources. You know, if I have 70% of the box available to me and suddenly I have 30, ooh, that's not good. Hardware failure. Oh, sorry, yes, please, question.
I mean, it's just a note, since it's just a few of us. I just find it very interesting to what you said about performance spikes. There was, I guess, multiple talks about this one in CPPCon. Someone from a company that basically a financial company, where they have a system where that is most of the time just idle.
Yep.
And then they have these spikes and they really need to be extremely fast. And they were talking about how basically you have to work against everything every design decision that is made in systems, right? Because everything is designed around being hot. And yeah, so I guess it's, do you in React, is it, do you have users who have this kind of thing, or is it just like, don't use React for that? It's not what it's
So we did have users like this. One of our users, can I say that? I think I can say that. They help run the internet in Japan. And they have a system where they have business hours. But of course, these are the official business hours where their service is open for business, but they have something else that queues transactions until business opens.
So but when business opens.
So yes, so between 9 AM, well, actually, no, that's not realistic. So after they've cleared the backlog, their main business hours between 9 AM and 6 PM, they're not that busy. But then 6 PM, the gates close and they start queuing again. And then it hits 9 AM the next morning, gates open, and suddenly all this queue of transactions are chucked straight into React. And you know, they get the classic every day.
Wow, yeah.
However, React can handle that, and I'll explain why a little bit later in the talk. Yes, another common one, hardware failure. In cloud computing, this shouldn't happen, but it does. One of the classic ones that people run with ephemeral drives. Somebody turned the box off. Oh, whoops, well, that's gone. But in real life as well, you have a box, it gets all pop, and you've lost it, and you've lost all the data on the box, and you say, oh no, it's the end of the world, except in OpenReact it isn't, you don't care. Which is kind of handy. And of course, the classic one, humans. Probably one of the most dangerous things ever in the history of IT. What could possibly go wrong? I never thought you'd do that. Wow, where did you get that from? So we're going to talk about how things like React scale, and this is one of the biggest problems people run into is they decide, yes, go on.
Sorry, just because so is React built on top of some consensus protocol?
Yes, we run on a type of sloppy quorum.
Sloppy quorum.
Yes, we are eventually consistent.
Interesting.
I'm not sure if you're familiar with CAP theorem.
Yes.
Oh, awesome. For everybody who isn't, CAP theorem is the idea of the ability to cope with consistency, availability, and things such as a network partition. Now, that gives you the essential challenge of if your system is always available, how do you guarantee that data is consistent? Because if one of your nodes goes down, for example, then you have an inconsistency, which means that by assuming if you want consistency of everything, then one of my nodes is down, so I can no longer be available. And of course, we then have the network partition example from a minute ago when I tried to do a balancing act. So yes, within CAP theorem, that's how we do it. So to get the close as possible to that, we have accessibility and ability to cope with network partition as our priority. And we are eventually consistent.
What is eventually consistent?
So let's say that this node receives for the write.
Yeah.
And the write comes in and you write back to the client and say, yes, I received that, thank you. And then this client says, oh, by the way, to these two, I received a write. And they go, okay, I'll update that now. Which means in the millisecond or so between this one telling these two and this one feeding back, if another client comes in and says, hey, what's that? You might have an old value stored. Because even though this one has the newest value, it hasn't written to the others yet. And that's a really tiny delay, and you can tune that in your queries. So for example, this does not count as a valid write until you have 3 primary nodes say, yes, I've written that. Is one of the tunings you can do when you write your queries. That has a slightly higher expense in that you have to wait longer for your writes to go through, but you can guarantee that the writes have gone through the entire system, and if somebody else can hit it and they'll have the most recent version straight away. That said, even if you don't do that, it's a couple of milliseconds, unless you're querying the same item again and again and again and again all the time, that probably shouldn't affect you. Right, so talking about system design.
Sorry, just to be sure, so you said
yeah, sure,
sloppy quorum.
Sloppy quorum, yes.
Oh, haven't I heard that? Interesting. Okay, yeah, thank you.
You're welcome. So one of the biggest problems that people have is when they design a system, they design a system on what they have now. Just that. Person, mirror, yeah, that works. But they don't think about when they go on and things suddenly get much, much bigger. I have a system, I have 100 users. Hey, it's great, it works on my laptop. I have 10 million users. Oh my God, everything has gone down. This is one of the biggest problems with scaling, especially things that scale quickly. Now think about it, you have people who put videos on places like YouTube or Vimeo or whatever. And they get maybe 5 viewers, 10 viewers, 100 viewers, and then suddenly they make a viral video back, and suddenly they've got 2.4 million viewers. Wow! This can happen in databases. Suddenly a user comes in and dumps a shed load of stuff with no warning, and your database is suddenly grown bigger than it holds, and things start falling over. Which is why you should always be ready to scale with your databases when you think about things. So, one of the things, and probably this is going to be the worst segue you're going to hear in this entire conference, is sharding. This is how you scale databases. I noticed a smirk there, thank you very much. So yes, a piece for everyone. So when you shard the database, you say, well, I'll give a piece to this node, and I'll give another piece to that node, and maybe some for you, and some for you, and some for you. Huzzah! So we now have all the little pieces, and they're distributed equally between all my servers. Yeah, pretend to as a server, please. Okay, and this is great, and it works. Everything should be great. You know, 2 partitions apiece, everybody's load is equally distributed, everybody's happy. It's a perfect distributed system. But then I realized things are starting to get busy. Maybe I need to add another load. I'm going to expand horizontally. So I bring in my extra node, and my extra node says, well, hey, I need a partition. Give me one of the shards, please. So we steal a shard from one of the other servers, and there we go. Problem solved. Really? Look at that for a second. So this one has 2, this one has 2, this one has 2, this one has 1, and this one has 1. So now we've got 3 servers that are really busy, and 2 servers that aren't really doing much at all. That doesn't sound very well distributed, does it? That sounds very unequal. Which is why when you're doing sharding, that's not the way you want to do it. Instead, you want to go a little bit harder. You want to hammer your system, and the jokes never stop, and we distribute it equally like that. And the thing is, with a large-scale distribution like this, if you have many more partitions per node, then let's say if this one's got 32 and this one here's got 29 and that one's got 33. It's not the end of the world, you know, you're probably, you know, plus minus 5–10% performance across all the nodes, because it doesn't need to be a perfect distribution, because at this scale, it's small percentage differences. In the previous one, you know, that's about, what was that, about 12.5% per partition. 5 nodes, 100 divided by 5, yeah. No, because 10%. I don't know, I can't do maths today, sorry. Yes, because there were 4 originally, so yes, it is 12.5% per person. Whereas now, you know, percentage probably about 1–2%, we don't care anymore. This is the level we don't care. But the other thing to do is, when things are distributed, you need them to be fault tolerant. Because you've got many, many different nodes, if one node goes down and everything goes down, by having more nodes, you're actually increasing your risk. You know, if any one thing can cause everything to fall down, then your uptime is nodes divided by efficiency of each node, probably worse than that, which is somewhat terrifying. So this is how fault-tolerant design should work. So let's do a CPU-based example. So if we pretend this is a CPU for different nodes, we're saying we're running OpenReact, but any well-designed distributed database should be roughly the same. So let's say server 4 explodes in a puff of logic. And of course, the load from server 4, which is now no longer functional, is then sucked in by the remaining nodes. So everything else goes up. Now, by this point in time, hopefully your system monitoring should have noticed that something is awry. So you'll have somebody who calls in and says, hey, we've got a problem with server 4. Can we send somebody in to go and fix it? So of course, we go on, server 4 is offline, so you send someone in, you send your highly trained engineer, or at least maybe your highly trained remote hands, and because they're as highly trained as ever, they go in and they probably unplug the wrong server. Hands up, who's done that before? Yep, done that before in production, many people aren't happy. So we've lost server 5 as well. Well, whoops. So what happens as a result? Well, the remaining servers then go over and take over the node from the 2 that are down, and it continues like this. So we have continuation, even with nodes going offline, because we're fault tolerant, the other nodes in the system are able to take that over. Now, that would work so far, but up to a point, people say, well, what happens if we lose another node? Because already these are nearly peaking. Well, I'll talk about that in a second, but first of all, I'll show a few quick graphs showing how things affect React. So in the same, OpenReact, in the same system we were talking about earlier, let's say we have a number of updates, and on the red line, what happened is we've killed one of the nodes, literally shut down, and then we start it up. And we notice how initially when the node goes offline, there's a sudden loss in performance. The amount of throughput we get, the operations per second drops. But then, first of all, when it drops, the other nodes will then spin up what we call virtual nodes, which will then cope with the missing nodes' work. And they will take it over and they'll work on that until the other node comes back. So that's why the initial sharp drop happens is, oh, a node's gone offline. And then all the other nodes have a quick discussion of who should take over which partition. They spin up extra virtual nodes. Everything comes back up to normal, which is why at this point here, the virtual node is now up and running. You see a sudden peak in performance there. And then they continue running until the server is then restarted. When the server comes back up, they then hand off all their information to the server. These are my virtual nodes. This is what they did on your behalf. Now you're back up, have the data back. And the server goes, great, and just takes over as if nothing had happened. Oh yes, sorry, I completely forgot to put node. I do apologize. Forgot to put lines in. Again, this one here is slightly more aggressive. This is where we took a node, we killed it, same as before, but then we were extra naughty, we waited for a bit, we then blanked the disks. So it's lost everything. This is the same as if you have a node or the hard disk catches fire, or if you're in Amazon, you turn it off with ephemeral storage and go, whoops, shouldn't have done that. Meant to press restart. And then, of course, we restart and recover. So we have the same initial cycle of everything goes off. Oh no, it's the end of the world. Actually, I've got notes of this one. So yes, we kill the node. The node is restarted. Everything comes back and it goes, hey, I'm back and I have no data. Whoops. So all the other nodes, instead of just copying across the differences between the data, they actually have to say, well, this is all your data that you should have, because we have multiple copies of the data in the database to make sure we still work when a server goes down. Go. And after it says that, yeah, okay, that's a lot of data to go through, we finally finish copying across all the data, the recovery completes, and we're good to go again. Which is kind of cool.
So in these scenarios, and especially I guess in this scenario,
yeah,
what is taking time until we go back to normal?
Oh,
so
right.
Is it like, I mean, I guess a RAF breakdown, right? Like, is it the network transfers? Is it actually reapplying the updates on the data? Yeah, just a breakdown would help.
All right, so generally what happens is node goes down, the other nodes panic and say, hey, this node's gone on. Well, don't really panic because they're programmed not to. But basically they say, we need to spin up a whole set of virtual nodes to cover the ones we just lost. And during that, that's data and a bit of network as they talk to each other and work out what needs to be done. And then they basically spin up the extra nodes, take over the load. That's the first bit. When the node restarts, it comes back up, says, hi, I'm back, but I have no data. So then the other nodes on the network will have to talk to the node in question and say, well, we know you're meant to have this. Do you have that? And for each one, it says yes or no, which is no for all of them in this case. So then they will copy across copies of the data to the node in question until all the data is copied across. So we have the network speed of actually physically copying the information from node A to node B. And then we have the additional write time of writing the data to node B because it didn't have that data. And then once that's all been completed, it will then pop back up and continue service as normal.
So it sounds like the main limit here is the network speed and the disk speed. It's not, for example, let's say reaching a consensus between the nodes, like who's going to take over, how they're.
That's generally predefined. Within OpenReact, everything works on a ring-based system, which is divided between the nodes, and every single node has a copy of the ring. So even if a node goes down, all the other nodes know immediately which partitions belong to the node that's gone down. And then there's a cluster manager, which can then tell them, you do this, you do that. It's meant to do the management, but generally it's automated anyway. So from my point of view, how would I do this? Well, I walk in, I pull the power cable, I pop open the box, or plug it in somewhere else, wipe the disk, plug it back in and say go. Start React.
Right.
That's it.
Yeah.
Human intervention is that level.
Yeah.
Everything else is fully automated. Yeah, it all handles that internally.
Yeah,
go for it.
Well, why not provide drop down, because other servers need to push data to the newly started. So
that's a very good question, and I will explain it for you on the next slide. So, are we okay to continue to the next slide? Excellent. Right. So, this is an example of. Sorry, I'm going to have to move this other window that's on my screen, otherwise I can't see things. So yes, if we look at how this works, here we see a zoomed in version of the failure from the previous slide. It shows how queries are served. And of course, we see that after we lose the yellow node, there's the initial blip where it comes back online. Things don't exactly look great. But as we can see, all nodes initially serve roughly equal patterned queries, but then we notice how the brown node and the purple node have to serve more queries. And the reason is that as we have n values 3, the number of copies we have is 3, then that means that these two have the other copies. So the yellow one's copy has gone away, which means those two have to make up, and those are the ones that serve the queries coming in, going out, based on that part of the data. Right. Yes, I want to continue from that. So now, if we run that in parallel, we look at this one. If we look instead at the user-facing queries served, this is very different.
What's the difference between user-facing queries and
The
queries?
previous one is total queries served is both user-facing queries and internal queries.
By internal, you mean between each other?
Between the nodes, yes.
Oh.
The nodes talk to each other.
Synchronize that.
Yes, so we ensure that everything comes. As I discussed earlier, let's say you write to this node.
Yeah.
This node then has to say to the other two nodes, yeah, you should write a copy of this because otherwise we don't have 3 copies. So there are both internal and external node traffic going on. So here we have the same scenario. And as you can see, the user-facing queries changes dramatically because it's not a case of this node has exactly the same data as these two. The data is instead distributed in a much bigger net mesh. So for example, I don't have enough fingers to do this. I'm going to grab some pens at random and see if I can do something. Here's 6, which is about the limit of my fingers. So maybe this one here has the same data as these two for one thing. And maybe this one here has the same different data. Maybe it could be for these two. So the pairing for each piece of data isn't necessarily with the same server for everything. So you don't just have 3 servers that then have the unique ownership of this block of data. You have multiple blocks of data which are owned by different servers. Therefore, it's not all of them that have to do the work of everything else. So, yes.
How is it here that, like here it seems that node 8 is serving queries at a time that in the previous plot you were showing was down?
Yes. This is where things start to become interesting. So let's try and cover this one. The way OpenReact works is essentially it has a reverse auction for every query that comes in. So query comes in and it says who can run the query, and basically it's a first grab. So I can do that, it's mine, which means the nodes that aren't doing much get it first, and they do more work as a result. Whereas the purple node and the brown node, they're very busy helping the yellow node restore its data. So as they're busy helping restore its data, they're quite busy, which means they're very slow. Who would like this? Oh yeah, I'd like one of those. Missed that one, missed that one. Well, I can get that one. Missed the next one. So essentially that means that they don't have to face so much, they don't serve as many user-facing queries. Therefore, they are more free to start providing data to the yellow node, which we're now restoring. Now, as they start to restore the data, it actually starts to come online. And the more online it becomes, so the more user-facing queries that the yellow node can do, the slower it then ramps up until everything returns to very close to how it was originally. That will then, if we extended this to about here, that will probably be almost identical as it was to when we started, which is almost an equal distribution between the 8 nodes.
So basically, at this, so when we see the first blip on the right-hand side, this is where the node is up and ready to run stuff.
Yeah, this is where the node has come up and says, "Hi guys, I'm back, but I don't have anything. Please give me something." And I've just been given my first piece of information. Yes, I know that one. That's the only one I know, but I know that and I'm going to serve it.
Okay. Okay. So immediately the cluster manager is aware of that and it can start sending things to that node.
Yep. When the queries come in, so the way React works, as it's a ring-based one, as I mentioned a second ago, when a query comes in, it comes into a node and the node says, "Do I have that?" And of course, that's a binary yes or no. And if it's a case of no, I don't have that, Okay, I'll look it up on the ring, who has that? And I'll send that, so let's pretend I don't have it, I'll send it out to the 3 nodes that should have a copy of it. And then whichever one responds first will then respond to me, and then I'll pass that back to the client. Which means that any query at any point you make to OpenReact will come back to you within at most 2 jumps. There's nothing else going in. Do I know it? Oh, yes, 1 jump. Or no, I don't know it, but I'll ask somebody who does. And it comes back and then goes back out to the client again.
And so if multiple servers are crashed simultaneously, does
Yes.
it means our data is lost?
No. Well, it depends. If you crash more servers than you have copies of data, then yes, you stand to have potential data loss. So within the standard default for React, you have 3 copies of everything, which means you can safely crash 2 servers and you can still guarantee you have the availability of all your data. Of course, if you boost that number to 4 copies or 5 copies, then you can do copies minus 1. And that's how many nodes you can safely crash without losing any data. In very advanced situations, you can actually make calculations of which nodes you can take down at the same time and not impact data availability by guaranteeing there's at least 1 copy everywhere. But you need to plan that and understand the very inner workings of how OpenReact works. So for new users, don't do that. But in theory, you could have a 20 node cluster and take up, I think you can take down up to 12 nodes offline. And that will still work even with only 3 copies of your data, if you know exactly how everything is distributed. But that involves a lot of thought processes. Do not do lightly. Just assume I have 3 copies, I can lose 2 nodes and everything's still good. Much safer. I've completely forgot where I was. Yes, I think I compare the 2 of these. There we go now. So we can see how the 2 of them start to come together. So the purple one still continues serving a lot of queries, and so does the brown one, but the closer that the yellow one comes back online, the number of user-facing queries it serves should then balance out and cover everything that was missing. Are we okay?
Sorry, could you explain again why in the bottom plot the brown and the pink are not serving much?
Yes, it's to do with the auction, I said. So because brown and purple are serving a lot because they're very busy, because they're serving the yellow server, mostly. Imagine you suddenly have to copy, I don't know, 16 terabytes of data to the server that's just come offline.
Right, so in this scenario, mainly the pink and the purple are serving the yellow. That's why we see this.
Yes, which is why we see reduced usage for those. Okay. And this situation, this auto rebalancing, this auto auction will actually happen all the time in React. So whichever server is busiest, what is the least likely to serve your response. And that will actually work well. So if you're in cloud architecture and suddenly you have to squeeze it onto a smaller box, it will still run. I mean, this is a nice thing. OpenReact can actually run with your CPU at 100% utilization. And if you lose a node, we think, well, everything's going to overload now because we can't take that extra load and stick it on top of here because it's already full. But instead, no, it will run this auction-like thing to work out who is least busy and then serve it. So if you do have to do that, it will still run, it will just run slower. Because you're already maxing your CPU. Of course, if you run it with availability, that's great. But generally, if you look at big IT companies now, they want to get the maximum bang for their buck when it comes to cloud architecture. So they want you to use the smallest box possible and max as many stats as you can, because that gives them maximum bang for the buck. I mean, if they're paying for 30% of stuff that's not used, why would they want to do that? And that's why we have this available. So even if you're running your box at max, you can actually afford to lose a node and it will still work, it just won't be as fast. The other advantage with this system is you can take nodes down for maintenance whilst the system is running. So the system will be perfect live, I'm going to kill node 4 now, boom, it's gone. And the system just takes over and nobody notices. You know, the users don't notice, even though we've just taken off a box for maintenance in the middle of peak hours and no one noticed. Which is really quite nice. I do the maintenance, I can bring it back up, it's all synced up, everything is back and running again and nobody noticed. So yes, this is another one here, node replacement. So I take the example from a second ago, I take my node offline, I have a brand new node I want to stick there instead, And we say, yeah, I'm going to take over what the old one had, particularly, and this is basically the same thing again. So we start node replacement. You are going to go away. You are going to be new. Go. Node replacement completed. It's basically the old node. Node 4 says I'm going to give all my partitions to new node, which I don't know, call it node 9, whatever. And node 4 gives all its partitions to node 9. Node 9 says, hey, I have all the partitions, let's go. And we're gone. And it works. Of course, this also works with horizontal scale up. So let's add a node. So we've got 8 nodes so far, we've added node 9. And everyone goes, oh, we've got a new node and we've already got stuff. Let's shuffle our partitions or shards between all the different nodes. Okay, these are yours. We hand them all off and we've got more performance. Yes, OpenReact also comes with some extra tools, active anti-entropy. What active anti-entropy does, apart from being a tongue twister, is it crawls through all your data quietly in the background and it reads it. And what React does is, can I put this in the slide? Yes, basically it compares differences. So if I've got 3 copies of everything, it will look at copy 1, copy 2, copy 3 and says, well, these 2 says A and this one says B. Probably A then, isn't it? So we'll then copy these 2 and overwrite that one. And suddenly we're back and everything's perfect again. And the thing is, this runs in the background. So big problems that you'll encounter, such as bit rot. What was the funky one? It's
where the eons hit them.
Yes, you know that one. Excellent, yes. So eons hit some server somewhere and changed a bit from 0 to 1. And I think was it Germany? Some election swung to a real remote candidate. And hardly anybody had voted for this candidate, but the candidate won the election. Simply because the bits suddenly flipped. And they won, which is really, really weird. But yeah, bizarre stuff like this happens in the world. Even just because you have it stored on one hard disk doesn't mean it's correct. Which is why having something like TikTok.AE, in this case, to crawl over all your data and then actually check, is this one and this one and this one the same? Ah, no, it's not. I should probably fix that. Is a really useful feature to have, because some people just use things like OpenReact because it can store massive amounts of data. Then people use it for backups. So here's a 4 gig backup. Go! And I'm not going to use that until an audit 7 years later. I wonder if that's still accurate. I don't know. Oh, look, it was a tar file and one of the bits has changed and the whole thing broke. Whoops. In OpenReact, that doesn't happen because it compares the differences between the 3 copies. So if one of your hard disks goes bang, you don't care. If one of the hard disks suffers, sorry, are you familiar with bit rot?
Bit rot?
Bit rot.
No.
Oh, sorry. Bit rot is a weird process. It happens more on magnetic media, but essentially the charge on a disk will mean that either data is a 1 or a 0. But for a very long period of time, if you don't use it, the charge will slowly degrade till it's not a 1, so we'll assume it's a 0. And that's called bit rot. So yes, if bit rot happens, then your data can become corrupted. Not because there's a major corruption thing or anything. No, it's simply your disks are old and your 1s became 0s. And you can't read it anymore. So yes, it goes through, it determines the correct version. So it goes through and says, yes, are you the same? Yes, you're the same, great. Or no, you're different. We're going to overwrite the one that's different because we don't trust that one. Make everything all the same. And everything's happy. Other than that, why else would you use OpenReact? Replication. So not only do we share data between the nodes in one cluster, we can also allow you to have multiple clusters that talk to each other and they can share the data between them. So yes, I'm going faster than my slides, I apologize. So it supports verification to multiple clusters. We have both unidirectional, which means I tell you everything and you just parrot that. And we have bidirectional, which is when we talk to each other and anything I learn, I tell you, and anything you learn, you tell me. And we can also do multi-direction as well, where you talk to you and we talk to everybody and everybody knows everything. And it's wonderful. Yes, also we can do it differently. So we can sync different data. For example, I wanted to, well, actually, let's just give you a logical example. Okay, all right, that's not on this slide. How annoying. So different queries can sync different data. So for example, a common use of this is, do you know GDPR?
From Europe?
Yes.
Yeah.
What is GDPR?
GDPR, okay. So there are data protection laws in Europe that say that private data about European citizens is not allowed to leave Europe. So that gives you an interesting problem. So let's say I run a huge US company, for example, it's not true, but for example, and of course, all my data is stored in America. I go, I've got this law I need to follow now. So I set up a data center in Europe. Then I have a data center in America. I say, well, we'll sync the data. Oh, we can't sync the data because the Europeans don't let us do it. How do we do this? So what we do is we set it up in OpenReact that this bucket or this group of buckets are GDPR data, which mean, well, you actually set it up saying, do not sync this bucket to America.
That's incredible. It's an incredible example.
Yeah, it's really practical. I mean, it's like huge companies, incredible legal nightmares because, well, the European data stays in Europe. Isn't that kind of easy? So yes, all the data that's generic data, we can sync between the US both ways. And, everybody knows everything and it's wonderful. But European data just stays in Europe, guys. And therefore, we're legally compliant. And even the application developers don't have to do anything. Stick it in the GDPR bucket. That's it. So yes, different queues can sync different data between different different clusters. And also the reconciliation engine that we use to sync data between nodes, you can connect external things to it. So a great example I heard about recently is you can connect OpenSearch to OpenReact, which gives you a really impressive search engine connected to a massively scalable database. And that means that you have the power of the fluffy search I told you before. Star A star. Go find it in React. Before that, you can't do that. React may have secondary indexes and stuff like that. You can do clever queries with, but star A star is just impossible. OpenSearch, on the other hand, it goes, hey, React, I'm going to index you. And then the OpenSearch indexes tell OpenSearch exactly where to look in React. And then it says to React, hey, can I have that one? And React goes, yeah, sure, there you go. And then we have it. And suddenly we have fluffy search in React. Isn't that great? You just plug other stuff into it and let it work it for you. Anyway, moving on. So system architecture, I'm going to give you a rather extreme example of how you can run multiple clusters together. So we'll start off, we'll say this is us. And let's say that's our main cluster, and then that's our other cluster. And by this point in time, I've forgotten who's who, so let's have some labels. Now, what we're going to do is we're going to say we have a bunch of labs that do research work for us. And each lab runs its own little React cluster. So, a bunch of labs. Ooh. Yeah, I am that crazy. This is going to be a nuts demo. So, we stick things out. So, we set up a user, we set up plus central A and central B as our two main Open React clusters. User is just us. We can be, we sit there, we use a load balancer and we talk to cluster A or we talk to cluster B. I don't care. And then we set up our labs, all have mini clusters. We set up replication between our two main clusters, which means everything on A is also on B and everything on B is also on A. So we play P1s know everything. And then we also talk to the individual labs. And each lab also runs a small cluster. But we use the same connection method where we choose what data we sync. So the labs will sync all their data to the central cluster. But the central cluster will only sync the minimum necessary data to the lab.
Is this a unidirectional thing you talked about?
So unidirection is just from one direction is only. So if we pretend that's not an arrow, let's cover that up.
Right.
That one rather.
Oh, yes, yeah. But I was just thinking that so the lab tells everything it knows to central B, but
Yes.
central B doesn't tell everything it knows to lab.
Correct. But some of the labs need to share each other's data, which is why, let's say this lab at the top left needs to share a tiny bit of its data with this lab here. They write to central A syncs to central B syncs just that bit of data with this lab.
Yeah.
So yeah, that's why these are bidirectional. Possibly it would have been clearer if I'd have just made them unidirectional, but the fact is you can still do that. It's kind of useful. It's like why I did it that way. So then from the user point of view, we talk to cluster to central A, or we talk to central B. We can do that directly, or we can do it using a load balancer. And it doesn't matter, whichever one I talk to will always have a copy of my data. Doesn't matter, even if I want to get the information from the lab at the top left, I can talk to central B, and because that's all synced up, I can still get my data. Even if we have an outage, then we can auto fall over to whichever one it wants, and it will still work. And this is a slightly extreme example of OpenReact in action, but the classic one of two big clusters running everything, this is very, very common. So from quite a lot of our clients, they'll either have a live site and a backup site. And sometimes what they'll do is they'll actually just switch their DNS to point to the backup site. They'll take the live site offline, do a huge number of hardware upgrades all at once, bring this back up, and then point it back at it. And they'll take this one offline and do a huge number of upgrades and bring that back up, and then they'll be good again. It's a very common one. We have some people who run live, or even one extreme example I saw in the US where they run East Coast, Mid and West Coast. They go live, and they all sync between each other to give people fast responses. Essentially, they use it as a CDN.
Yes.
Content delivery network.
Oh.
So you'll talk to whichever data center is closest to you. Yeah, but there are lots of really creative uses for React, and this is just one of the ways you could do it if you chose to. You could even have it so maybe this lab doesn't need to receive any information at all. So this one here, just this one, unidirectional. It's entirely up to you and your imagination how you go about it. So yes, we talked about why I think OpenReact is absolutely awesome. When should we use it? So what kind of businesses use it? Financial institutions. Yep, definitely one of our large customers is a European bank. It's definitely in use because we help support it. Government organizations, as I mentioned, we actually work with some. E-commerce, again, one of our customers is Japan's second largest e-commerce provider. Manufacturing, think about it. I want to know where my inventory is. I want to know where this is. Is this just in time? Yes. Messaging, people don't know this. Originally, Apple actually used React back as it was in the day for iMessage. You know, this stuff scales incredibly well. Line, the most popular messaging app in Japan, runs on OpenReact. You know, it seriously scales and it's really good. It's built on Erlang, which is originally a telecoms protocol. And because it's a telecoms protocol, of course, multiple messages going everywhere all the time. Hey, speaking our language.
Oh, so all of so OpenReact is written in Erlang?
It is indeed.
Maybe so. Probably one of the biggest databases in Erlang ever, right?
Yeah, and possibly one of the biggest databases on the planet, to be honest.
Sorry. I meant also code bases.
It has a pretty large code base, but then again, lots of the competitors are closed source.
Right. Yeah.
So we don't know quite how big they do stuff. And of course, yes, new one, popular one, IoT. If I have 10 billion devices that phone home once a day, where am I going to store that? A huge distributed database. I want to know what's going on all the time, and I want to make sure my IoT devices have somewhere to write to. So, usage advantages. So, cloud or commodity hardware, yes. I can run it in Amazon, I can run it on Azure, or I can run it on a computer sitting on my desk. You can run it as a single node. Do that only for development, please. If you lose your node, you lose everything. Yes, it's horizontally and vertically scalable. Horizontally scalable, I can just add more nodes and I get more capacity by doing that. Vertically scalable, I buy a better box, or maybe I upgrade my box, I add more memory or whatever. So yes, we talked earlier, it's fault tolerant. I lose something, but I can still recover from it. It's eventually consistent. I write to this one and these two will know about it pretty soon afterwards. Geo-redundancy. So if I have a cluster in Asia and I have a cluster in Europe and I have a cluster in America, then even if one of the clusters goes down, the other two still work. So I just redirect my traffic to my other two clusters. Compliance, as I said there, GDPR, also the Cloud Act. Anybody familiar with the Cloud Act? Oh, right. This is a very special piece of American legislation from 2016. It basically says that the US government can talk to any cloud provider and say, give us your data on this. And the American cloud provider is legally required to say, yes, here you are. but they are not legally required to tell who the person whose data is being given. Now, in the US, that's pretty much standard. The American government gets everything they want from America. Yeah, great. The interesting thing comes when it's a European company, or a Chinese company, or a Japanese company. The US can say, well, hello, Amazon. You know how this famous company from your country tends to do stuff? And I know that they're based in Ireland, for example. We'd like to see their data, please. And because Amazon is a US-based company, Amazon says, we don't really want to, but yeah, okay, here you are. And the Irish company knows nothing about this. I think that's absolutely terrifying. But legally, that's okay, which really, really scares me. Which is why, yeah, a great way to avoid the Cloud Act is run on something that's not run on Amazon servers or Azure servers or Google servers or whoever, as these people are really scary. Do not have people steal your data unless you want to give it to them. So yes, that's something you really want. I mean, run it on your own box. That's probably the safest thing to do. But yes, compliance. So if you have to avoid things like this for legal reasons, for security reasons, whatever, maybe you're a secret research project for your government. Do you really want to run that on something where a different government can steal your data? No. And there's different reasons why you should think about using something like OpenReact. Privacy is the key to going forwards. And of course, security as well. OpenReact can run in an air-gapped environment. Let's say someone like DynamoDB do that. I'd like to see you run somewhere with no internet. Of course, I've got my own boxes, it works for me. I've got OpenReact, but you got Dynamo? No, that ain't gonna work there, is it? Let me, air-gapped, no, that's not gonna work. Right, so moving on. Why is InReact insecure out of the box? And this is a very obvious one when you think about it. It's really hard to set up if it's not. This is a decision by choice. Yes, why is it insecure out of the box? Because if you don't know what you're doing, OpenReact is a nightmare to set up if you want it to be secure straight away. However, to get it up pretty easily, you choose your package, you install it, you say start, and it works. I can't see things much simpler than that. I admit it, you do it from the command line, which some people are scared of these days, but if you're okay with the command line, that's it. Download, install, start. And that's why we keep it insecure out of the box, because we want to keep it easy. But how do we go about doing things? So what is insecure within OpenReact? First of all, we have a service called EPMD. I'll explain these in a minute. We then have HTTP queries, and we have user permissions. These are factors that we can actually control. We can kind of control within React. So EPMD. EPMD stands for the Erlang Port Mapper Daemon. I can never pronounce that. So what it does is it basically talks to all the other nodes and it says, hey, I'm an Erlang node. I have a whole bunch of ports you can talk to. These are my ports. Come be my friend. And that's what the Erlang Port Mapper Daemon does. Problem is, it tells anybody, which is a bit of risk when you think about it, especially as it's required for OpenReact to run. It communicates via a shared cookie. So, there's a little bit of security. What's the password? It's this. Oh, okay, here are my ports. But it's a shared cookie, so all the nodes have to know the same cookie. It's a bit like Alibaba and the 40 Thieves. Open sesame. I know the secrets now. So, and the problem with React is the default cookie for 17 years is React. Which means that when you download React and you install it and you say go, and it says I'm React. Hello everybody, I'm React. Come and talk to me. Which is useful because it's easy. It's not particularly secure, though, really, is it? Because if that's published on the internet everywhere and for 17 years, default cookie is React, then everybody comes to a React system and go, hey, I know what your cookie is. And probably they're right because many people don't change it, which is pretty scary. Right, so yes, why is EPMD a risk? So a malicious party gains the cookie, or you use the default cookie, of course. So what happens, they can then communicate with the other nodes on your system. In fact, they can communicate with all your nodes on the system, let's be honest. What can they do with that? So they can do nasty things, they can overwrite low priority functions. Which means they can inject malicious code, which means they can even go from there to issue malicious Erlang commands. And finally, they can use Erlang to issue malicious OS level commands. So we've got this one here where we can say, hey, just open a full shell script, shell prompt to me, and I can talk directly into your system and do whatever I like. We've got malicious Erlang commands, so I can silently corrupt your data in the background. And I can also issue malicious OS commands and do all kinds of nasty stuff. As the HTTP queries, so OpenReact listens for HTTP requests by default. The HTTP API supports create, read, update, and delete standard CRUD operations. So why is this a risk? Well, it's HTTP, isn't it? HTTP is not encrypted. Third parties can read the data on the wire. Anybody here played with Wireshark or TCP dump? Yep, yeah, it's good fun doing that, isn't it? You can say, hey, they said that, wow. Third parties can also issue curl requests. Have anybody used curl? Pretty quickly, can you explain what curl is?
Basically, wget.
Yes, basically wget. Yeah, you can actually use wget with React as well, to tell the truth. So yes, and OpenReact, of course, you can issue commands directly. So I say, hey, create me a new bucket that does this, or hey, read that bucket for me. And it will say, yeah, okay. It allows for potential data leaks. Of course, if they can read your data, they can steal all your data. It would take an incredibly long time with curl requests, but yes, it's possible. And again, it allows for potential ransom attacks. If they have curl requests that do updates, I can read your data, I can run an encryption key on it, I can then update your data with the encrypted version. And if you've got 10 million keys or 10 billion keys, which is quite common in React, it may take a while before you notice that, at least 5 million or so have been encrypted without your knowledge. And of course, there's user permissions. So by default, React has one shared user for everyone because that's easy and simple. Which means anyone can read anybody else's data. Of course, that also means anyone can update or delete anyone else's data. You'll see where we're going already, can't you? It gives us potential data leaks. And also for ransom attacks in the same way. If anybody, yes?
Oh, no, sorry, I just wanted to, this was for a question for the end of this, but so basically your point is that to secure OpenReact, you have to undo or basically fix all these.
These and more.
Okay.
Yes, it's an awesome database, but things have to be simple for users to get into it, because if you have to go through a nightmare of security before you got to play with it. For developers, they don't need to make a secure system. I mean, they're developing, for crying out loud. It's meant to break and be horribly wrong and easily corrupted. In production, yes, you seriously need to think about this, but if you're developing, no, use it, have fun, use one node, it's insecure as hell, you lose all your data, but you can still talk to it and it still works just like it would in production. So, remedies, how do we fix this part of issues? Well, first of all, EPMD, well, shocker there, change the cookie so nobody knows what it is. It's that simple, I changed the password, it's not Open Sesame or React anymore, it's something else. So yes, technically this is security by obscurity, but then again, your system is unique to you or your organization. If nobody in your organization shares that data with anybody else, and you've got, I don't know, maybe a 64-character long cookie, that's going to be really hard to brute force. Hopefully something on your system, someone will go, hang on, something funny is going on here. Before, they've gone through however many a million or billion transactions it takes to finally guess the right cookie. Unless they're very lucky from the first time. From there, HTTP API, well, install SSLs. And suddenly we can then have a secure connection. So that means that, yeah, by encrypting the connection, people using Wireshark or TCP dump cannot listen to your data on the wire. However, if they're still able to do curl requests to your system, they can still do secure curl requests to your system. which is still a bit of a risk. We need to think about that one. So, user permissions enable React security, which is a function within OpenReact. You can prevent access to things. So you prevent access without a valid user. And suddenly, unless the person who's trying to attack your system knows the username and password, or maybe you do IP-based restrictions, or maybe you do PAM-based restrictions, or however you want to set it up, as this supports quite a lot of different options. Only people who fulfill the security restrictions are able to access it. And you can still lock down individual stuff. So even with this username and password, I can only access this bucket. I can also access this bucket, but this one's read-only for me. Whereas somebody with higher permissions would be able to write to both, or maybe write to this one, but not even be able to see this one because it only belongs to that user. Which, even from an application perspective, still works. If you have a part of the application that just reads stuff all the time, why does that user need write permissions? This function just reads stuff. Why does it need to write permission? It doesn't. So don't give it to them. Again, permissions, lock them down. Minimum needed only is the safest way to do permissions in this case. And if at a later date they need to do an additional feature, I'll enable it then. But of course, that's still not enough. As we saw, I mean, if they have valid credentials, they can, well, not just valid credentials, there's still not enough overall. So, didn't we just secure everything? I mean, we fixed EPMD, we encrypted HTTP, and we blocked access by requiring valid credentials. Isn't that enough? Well, connections to OpenReact are encrypted. Anybody see where we're going with this?
You can connect through OpenReact to something else.
And we require valid credentials. But OpenReact is a distributed database. Think about the slide earlier, where we had, this is the huge amount of traffic going on. This is the amount of user-based. It syncs data between nodes. The Erlang connections between the nodes are not encrypted, that's why. So even though to the outside world we're impervious, if we've got node A talking to node B saying, hey, you got that data? No, but I'll give you a copy. That is not encrypted out of the box. Oh. We've done all this encryption work and we're still not safe if somebody's on our network. Again, OpenReact runs on regular Linux servers. We don't care, it can be cloud, it can be local, wherever you want. But of course, what that means is that it has a large code base and it uses many, many different ports because we have to sync data all over the place all the time. We need a lot of ports to be able to do that. So in IT, as you probably know, all the time there are new attacks that are coming up, things that we've never heard of before. And even the latest version can be vulnerable to zero-day exploits, which is always a risk. You never saw this one coming. Which means that third parties may try to access the ports in OpenReact directly, which is always a worry. And finally, what is the other problem I managed to analyze? Well, OpenReact needs storage. We talked earlier about hard disks blowing up. Many companies run their OpenReact on their own hardware. You see where this is going yet? Physical hardware can be stolen. If somebody breaks into your office and steals your server, there's not a lot you can do about that, is there? So even without open username and passwords, you can read data from stolen storage devices directly. If I rip the hard disk out of your server, I plug it into my laptop and I go, hey, what's on here? I can still read your data. Because I can't read it in order. I have no idea that this key is this bucket is here. But I can say, hey, there's a whole bunch of data in here and I can read it.
Well, this data is read in a certain way by OpenReact.
Yes.
Right? So potentially an attacker won't be able to set up React and just read the data.
If I only steal one node, that becomes much harder. I can read the data on my single node, but that's part of the cluster. I mean, the thing is, yes, they could technically set up OpenReact and start it again. But then again, if I have, for example, a BIOS level password or something, I'll need to bypass that to get into my system.
Yeah.
Yeah, there are many different aspects to security. I mean, no matter how hard you try, things can never be 100% secure, and that's really sad. but you can do your best to get as close as possible. So, thinking about the ones we talked about a second ago, what else can we do? So, securing even more. So, connections between nodes are not encrypted. What do we do? Well, something like point-to-point VPNs or tunnels. If my encryption between here and here is fully encrypted, so if my connection between here is fully encrypted, do I need to worry about anything else? It's encrypted. People can't read my data on the wires, it's encrypted. Third parties accessing server ports directly. Well, firewall. Block access to everything you don't know. Physical hardware can be stolen. Well, encrypt your OS file system on your disk. Sorry, that is the same thing. Encrypt your OS file system or your data within REAC, not within OpenREAC. So yes, tunnels or VPNs. So from OTP 28, which we're sadly not at yet, OpenREAC, because of the huge amount of development work we need, upgrading OTP version takes us time. So we're usually 2 to 4 versions behind the latest. So OTP 28, which hasn't been released yet, or at least if it has, I'm not aware of that. It will have internode encryption out of the box. Woohoo! So we don't need to worry about that. That means all nodes, all encryptions going this way, all connections going between nodes will be fully encrypted. We don't need to wonder about tunnels or VPNs. But in the meantime, we could use something like Tink, which is an open source tool. You can download it, literally go to Debian or Red Hat or Docker Linux or whatever your thing is. Do apt install or yum install or DNF install or whatever, look for Tink and just go set up a tunnel. It's surprisingly simple to use. It's not incredibly secure, but it's a great thing to start with. Another option you could use, Strong Swan. Again, it's something most places will allow you to download directly, and it gives you IPsec between your boxes. And IPsec is still considered a pretty good world standard at the moment, so you have IPsec between all your nodes, and that should be safe. Notice should. I never trust these things. Should be safe until somebody cracks encryption for that. Firewall restrictions. Well, your OS will naturally come with a firewall. I mean, if your OS doesn't have a firewall, this should not be in production. Let's be honest. But you can also use third-party ones if you want. And basically restrict your firewall to known IPs and relevant ports only. And I do mean that. For example, the application layer needs only React's API. It doesn't need EPMD. Whereas the logical one people do, well, these are all the nodes I know, so I'll open the same ports to everybody, and no. Make sure that only OpenReact has OpenReact necessary ports, and the application layer is locked down to the API only. And don't forget SSH access for people who need to get into the boxes legally. Encrypting your data. Well, this is the standard encryption at rest. We just did encryption in transit for tunnels VPNs. Encrypt your data directly, for example, within OpenReact. You do it, well, not within it, to be exact. In your application layer, you write an encryption algorithm. You then take the data in, you encrypt it in the application, then you store it in encrypted form in OpenReact. And then when you read it back, you then decrypt it and pass back to the user. Is one solution you can go for, which means that even if somebody does steal your hard disk, it's actually worth this because they need to steal the application as well. Most people, they'll go for the other option. I guess that will impact free search though. Even if you do searches with indexes. If you're doing a fixed search, for example, find me something that's indexed with index ABC, because the encryption of ABC is the same, that's easy. But if you want to do find me all data happening between 2011 and 2020, that's a fluffy range and you can't do that because the encryption for that will not, the encrypted value of that will not be searchable. But if it's a hard one, just get me everything from 2011. Yes, that's doable, even if you encrypt the data on disk. And the other one is, yes, encrypt this directly, file system encryption by ZFS, I believe will offer that out of the box, which is available with many operating systems these days. Of course, if they access the box while running, a bit like what you said earlier, if they steal your server, decryption is automatic. So as soon as you turn the box on and you log in, then decryption just happens automatically, and yeah, they can get your data again. Which is why you might want to encrypt via your application, but then it limits your functionality, so you have to choose the lesser of two evils. I mean, to be honest, with all the things we've covered so far, that would make things ridiculously secure. but it's a pain to set up, and often organizations, even large famous ones, will choose not to go to that level of security just to make it easier to use. Many places will just go, well, the whole thing is firewalled off, nobody else can access it, so we're safe. Okay, if you say so, fair enough. So if we follow this in a logical way, so what did we cover? We have an insecure application. And these rules, I think, will apply to generally anything, not just OpenReact. So we take our insecure action and say, does it come with any security tools? Can we actually turn anything on that fixes stuff for us? So in our case, OpenReact, yes, we use the tools. So we changed DPMD, we added SSLs, we created user accounts, etc. So next question, is it fully secure now? Well, no, it wasn't. So we then have to go in, we use third-party tools to fix the insecure areas. So we fixed it. So is the OS secure too? And this is one people may not automatically look at out of the box. My application is secure and they just hack the OS. Whoops. So yes, make sure you secure your OS in the same way. Identify and fix insecure OS areas and test. I cannot emphasize this enough. Test. If possible, pay for a third party to come and test, because people generally only check what they know about. They don't know what they don't know about. So we've tested. Is it secure? We've gone through all these steps. Is it secure? No, it's not. Whoops. We tested and it wasn't. So we go through again. And we repeat the cycle. So we go through and it's fully secure. Yep. Let's run a test. Yeah, that seems to be okay. So is it secure? Yes. Really? Let's do it again just to make sure. And this is what I mean. This is why testing is so important. There's a whole bunch of tools. Read things on the internet. Spray your ports with all kind of garbage data just in case there's some weird vulnerability you haven't found yet. Do all kinds of stuff. I mean, hire a penetrations tester to come break into your system and tell you how you do it so you can fix it before somebody malicious does that. Things like this. There are millions of different ways you can make sure you go again and again and again to have one of the most secure things available. And finally, if you're really, really sure you're secure, we can finish and move on. So, in a brief one, a wrap up with Q&A. So, wrap up. Introductions, yes, we talked about today. Introduction to TI Tokyo, that's us. Huzzah! We do OpenReact, among other things. We talked about OpenReact, why it's an awesome database and why you should use it. When you should use it. Why you should use it. Never mind. We talked about potential threats to OpenReact, both the ones that come naturally with the insecure state and then other ones that can be OS affecting as well. We talked about fixing those with built-in security tools. For example, most operating systems come with both a firewall and the ability to encrypt your disks. And of course, the tools in OpenReact as well. We talked about using external tools for further security, for example, a third-party firewall. Other things you probably want, packet sniffers on your network, maybe even a honeypot if people are feeling creative. As you go on to talk about other areas, oops. And yeah, that actually brings us to the end of our talk for today. Yes, I've been Nicholas Adams. Please feel free to contact us, check out OpenReact, do all kinds of other stuff. Whilst I'm here, you see the survey at top right. We actually have a sweepstake. In a very efficient way. I prepared everything talked so well that we actually have our own doll, Chio-chan, who was going to be our prize and surprise, and I was going to show you here, and I very carefully left it on my desk. So I'm afraid I had to get a colleague to take a photo for me and send it to me, or such. Rather embarrassed about that. But yes, that's your prize, Chio-chan doll, if you fill in the survey. I'll take you back to the previous slide, so that's where you can get the survey from. Yes, if I actually had it here, I could just show you and not need the extra slide. That's slightly embarrassing.
Thank you very much.
Yes, thank you very much. You've been a great audience. Any questions, please?
So just to be sure,
Yes.
OpenReact it basically uses the default operating systems of the servers. There's no file system layer that it depends on or something.
Nope. So over the years, OpenReact has run on everything from what is it? XT3, XT4, there's XFS was one, ZFS. But you can run it in all kinds of stuff, and you can run it in all kinds of configurations. Some people, for example, run it on JBOD.
JBOD?
It's a form of RAID setup. JBOD is a real cheat. It's literally just a bunch of disks. And what happens is you just plug in a bunch of disks together and join them together. It's one huge disk. Yay! Isn't hardware amazing? You can use RAID if you want to, but then again, if your React nodes are, you can fail them and then bring them back up. Do you need to use RAID as well? I have 2 copies of my data on disk and I have 3 copies across my cluster. Up to you, really. You can, yeah, go for it. Why not? Or you can choose not to. I mean, the plus side, if one hard disk explodes and you're running RAID 1 or something higher, then it will still run, which means you don't have to take node down to maintenance. But yeah, that's the flexibility of it. I mean, one of the huge savings that people find with React is many big systems, especially professional ones. I'll give you an example. There was a huge system in the in the UK that ran on Oracle. And that was a big, expensive system. And one of the biggest issues was that if one of the databases went down, if one of the servers went down, they had to pay for somebody to be able to get to site in 15 minutes and fix it, which is a huge cost. So what they did was they switched from Oracle to OpenReact. Well, actually React as it was back then. And even though React possibly cost a tiny bit more to run than Oracle, the difference was that OpenReact, a node has failed. Okay, yeah, I'll fix it when I'll be there next week. And it just works. So from the savings they made from not having to have all these people here on SLA and licenses and train people and all the rest of it, they made, well, I can't say they made a killing, this is a government service, but they made huge savings from this, which meant that the OpenReact one is a no-brainer. You know, if you have to pay less, you know, one node goes down and you don't care, why do you need these, 15-minute SLA? No, my SLA is, next Tuesday. My node has gone down on Friday night. What do? I fix it next week. Doesn't bother me. Doesn't bother the system. It just works. Anyway, this is some of the power of OpenReact. With failures and things coming back, that's exactly how it can take over. I think I might have gone slightly off track there.
I guess another question I have is, what do you think are the use cases that OpenReact is not good at? Like, what do you think is, I guess I would come to you and I'm like, hey, this is my use case, and you'd be like, yeah, maybe OpenReact is not that good at that.
That's very much down to your thought process. I mean, if you have a system that's essentially a whole bunch of fluffy lookups all the time, I'd probably recommend you do that in SQL in some way.
So by fluffy lookup, do you mean like joins and stuff, or do you mean like?
That's an interesting question. There's actually a paper I wrote on SQL and NoSQL and how to mirror between them, but unfortunately that's not public yet. How can I say that? Yes, so things like joints and so on, as I explained earlier, you can do massive parallel lookups in OpenReact.
Right.
So you don't actually do a join in OpenReact at all. What you do is you grab everything in this area and grab everything in that area, and then join them together yourself at application level.
At the application level.
Yeah. Which is why OpenReact, probably one of the strengths of OpenReact is reads and writes are blindingly fast, that they leave SQL in the dust.
Right, but isn't then the application going to be very slow, like doing the join?
Well, think about it. If my application has all the information it needs in memory.
Yeah. Well, many times it may not even fit.
It depends on the entire scale of the stuff you're doing.
Right.
If you do need to suck in huge amounts of data, I mean, as I mentioned at the start, we can do things in MapReduce to actually have it done on OpenReact, where it sucks all the data into a central pool and spits it back to you. That's also perfectly doable, and you can do that. But if you go wild with that, you can shoot yourself in the foot.
I see. Huh.
But if it's a situation where if it's something that's, of course, no matter how you look at it, this is an SQL target, then you can probably do it in OpenReact, but we wouldn't recommend it.
Okay.
Yes, SQL, it's absolutely awesome for some stuff, and I would strongly recommend it for some applications.
So basically, would you say that OpenReact is a very good target when the queries you have are not fancy? They're not like the equivalent of, I don't know, a 10-line SQL query. It's just, I want to read massive amounts of data and I have many queries that read massive amounts of data.
Yeah, I mean, in OpenReact, we have a thing called secondary indexing. So you can actually tag your data as you put it into the database with things we can then search for it with. So we can do basic range ones, assuming you haven't encrypted your metadata, of course. Assuming you haven't encrypted your metadata, you can do things, for example, find me everything between 2010 and 2020. You can do that, and it will go through and search everything for that. You can do, for example, the autocomplete. So let's say I want to type in somebody's name. Let's say the name. Let's go for a short one. So a place name. So I type in T, and then it will. Then we do a range search in background between TA and TZ, and then that will autocomplete that. And then if you type in the next letter is O, then it does then TO, and then a range query between A and Z, and so on. So you can, things like autocomplete is all we can do. It's just when you want something very fluffy, so find me a city with a letter O in it. It's pretty hard to do in OpenReact. Whereas to do in something like a ranged one, we can do that. So again, if you just have preset indexes, so let's say let's go for a ridiculously simple one. Let's say I'm doing a menu for a cafe. If you use OpenReact for a cafe and it's a single standalone place, you'd probably be nuts, but it's the kind of thing I do. But just for proof of concept, just to show you can. So I'd probably have a secondary index called coffee and another secondary index called tea. They'll list me all the coffees, and then it will hit the secondary index and then list every coffee in for example, I don't know, Kilimanjaro or whatever. And then list me all the teas, and I know maybe goes Assam, Euralia, something else. And that's so you can do your one-to-one matching of this is guaranteed to be in this category, and you can assign multiple indexes as well. So we could do teas, and then we can have good for hot and good for cold. And then we can say, yeah, this tea made great hot tea, but it's pretty terrible at iced tea. Whereas this tea is pretty good at hot and cold. So you can give me all the teas with this index, and you can do that. It's all how you set it up. So the very fluffy searches it suffers from, but slightly more accurate searches that are actually easier to express, it will do that pretty well.
Thanks.
To go back to the credential part.
Oh, sure. What's that?
Yeah, very good presentation, and I follow most of your talks. So I'm a distributed system newbie. I still want to.
Is this far away? Yes. Here we go. I know credentials was the one you asked, didn't it?
Yeah. This time, I'm not fully understand.
Hang on, that's not the right one.
I think the second bullet point.
Yeah, I mean, the requirement need a credential, but why not add a credential between each two nodes, like when there is synchronous?
At the moment, that's not an option. It's to be very simple. But at the end of the day, it's the same as the EPMD thing. That's again essentially security by obscurity, even if we do that, which is why having an encrypted connection would work. At the moment, the connections between the nodes are not encrypted. So if I say, hey, this is my username, this is my password, please give me this data, then anybody who's listening on the wire can go, oh, well, look, there's a username and password and the request for data. And then I know what your credentials are. Which is why we want to encrypt the tunnel between the nodes. Well, sorry, either set up an encrypted tunnel or from OTP28, have Erlang naturally encrypt it for us. Does that answer your question?
So in EMDP or
EPMD, yes.
EPMD, so when write use cookies like to do a broadcast to everyone.
It doesn't so much broadcast to anyone. It's the case of if you talk to it, it will tell you. So we go, hey, you're an EPM daemon. Hey, EPM daemon, what do you have? Then it will tell me everything it has.
I see. Thank you.
You're welcome. Nice. And I think that brings us slightly over time for today. So thank you everybody for attending.
Thank you very much.
I should probably check whether any questions. There's somebody who put something in the chat. Excuse me for just a second, I've been very ignorant. Oh, and somebody else says thank you. Awesome. There we go. Thank you very much, Peter. Okay, yep, so I think that brings us home today.
So I'm going to end the call.
Yes, please.
By the way, there's an adapter here. Is it from the university, or do you think somebody may have forgotten it?
No, I'm adapter. Well, I don't work here, so I really don't know.
Maybe it's impossible to get it out, so probably it's from
Okay. Well, that might be kept here so third parties from with foreign plugs can plug in.
Yeah, actually, I really need such an adapter.
Nobody's looking. We're not recording anymore.
By the way, are you living in Japan?
Yes.
Wow, how's that?
Hot. Although actually at this time of year it's not as hot as here. The summers are a nightmare, the winters are ridiculously dry.
Oh, interesting. Yeah, because here I was very surprised when it became very humid here.
I mean, having just finished Japanese summer, this was pleasant. Ooh, one last thing before I forget. I've used Chio-chan everywhere, and this is what our new website will look like, but we're still in the process of updating it. So if you actually go to our website now, it doesn't look like this at all. Which is why you go, hang on, that guy talked about Chio-chan and had, this go on the slides all the time. She's not there. Why? It's not live yet. Sorry.
No, that's cool. That's nice. I mean, it's very nice that we learn about OpenReact. I had never heard of it. Yeah, I don't. Do you know why it's not more known?
Yes. When Basho died, as it was a famous venture capital company back in 2017, the world press went absolutely nuts with Basho is dead, therefore React is dead. And after we actually brought it back from the dead, the press wasn't interested. So it's used in a surprisingly large number of companies around the world. The chances are that in your day-to-day life, you will actually touch React at least once or twice a day. So as we're not recording anymore, is that still live?
Is this the last stream? Maybe just click.
Yes, we're still live.
Oh wow.
In that case, I should probably, I should drop out. Maybe. Are we good to go?
Yeah, also the video.
Video as well. Oh dear, that's not very good, is it? Is that working now?
Yes.
Okay. Do we just continue? Very well. Well, sorry for the online people who missed that. You looked at some slides populating themselves. Very briefly, yes, talk about who I am. This is my company. I work here. Why are we here? Well, we did training, so we can kind of teach a little bit. And we do stuff with React, which then became Open React, and we help make stuff, and it's cool. So, what is Open React, which might actually be relevant to quite a few people here today? So, let's break it down. What is a distributed system? Anybody? What's a distributed system? Anyone? Yes, please.
System that runs on separate computers.
Very good, thank you. I like that. That actually works very close to what I got. Anybody else? Something about distributed systems?
That's pretty much the same answer.
Very well, okay. So let's put it in the context of distributed database. So what we do, we share the data between machines. We commonly store multiple copies of data. And the reason you do that is, let's say one of your nodes goes down. That's strange, I lost a drink. One of them goes down, you've still got other copies elsewhere, so things still work. So rather than having one node goes down, everything dies, you have one node goes down and oh, I can still work. It usually will have some ability to scale. You can either scale by having a bigger box, vertical scaling, or you can add more boxes to scale horizontally. And of course, because it's a distributed system, it can process vast quantities of data because you can just stick a lot of boxes together and they work. So, of course, when you build a system like that, what could possibly go wrong? Well, conflicting writes. If I'm processing, I don't know, 1 million queries a second or 10 million queries a second or whatever, I mean, they're quite common. 2 conflicting queries come in at the same time. I have a list with 400 items, maybe item number 11 is different between the 2 lists, but the rest match. What do I do? That's a conflicting write. Network partitions. Do this, pretend this is my cluster, pretend there are 5 nodes please, but I just don't have that many hands. So let's say there's a network fault, one of the switches breaks or a cable breaks or something, so suddenly I have a partition where I have 2 nodes here and I have 3 nodes here. If both systems can continue running in parallel to each other and continue serving data, that's great, but what happens when you join them back together? That's a network partition. Performance spikes, well, that's self-explanatory. Suddenly everybody dumps their data at once. Oh, everything exploded, game over. Hardware failure, again, classic one. It runs on hardware, hardware grows old and dies. That's life. And of course, the most dangerous thing in computing in the world, humans. So, let's talk about that in distributed systems. So one of the biggest problems we see in distributed systems, and this was also related vaguely to performance spikes, is scale. People make a great POC. Hey, look, this is my system, it works. Yay, I'm happy. And then suddenly there's huge amounts of growth and it's not quite ideal anymore. So, in possibly the worst segue you will see in this entire conference, we'd like to talk about sharding next. And what is sharding? Well, when you've got a database that grows very rapidly, you need to think about who has which pieces. So if we pretend that our company mascot Chio-chan, who is here, 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 and here in various poses, is a server, and we look at the broken mirror and we say, well, you can have a piece, maybe give you 2 pieces, and then you can have some, and everybody can have some. And look, we've got 4 people holding 2 pieces apiece, that's all the pieces, so we are completely covered, and everything's great. That's a nicely distributed system. Every single server has the same amount of load shared between all of them. Everybody agree? Yep. Okay, so let's say, well, everything's getting a bit busy. I need some more capacity. I know, I'll add another node. So we add another node. And we say, well, I got no partitions. Give me a partition. So we get a partition. Is that now an equally distributed system?
No.
No. How can we make that a equally distributed system?
So number of nodes, number of pieces, or maybe equal number of workloads to everyone.
yes, well, to do that, I then need to grow that to 8 nodes. But let's say I don't have enough capacity then, what do? I introduce the 9th node and we're back where we were.
And like the middle shots.
Exactly, thank you very much. Yes, that's the way we do it. We shatter things a bit more and we give everybody a shed load of nodes and we're all good now. And this is the thing is, in one example we had a second ago, we had 4 nodes with 25% capacity each. But then when we added the 5th node, we then ended up with 2 nodes that only had 12.5% of the total amount. With this one, even if the sharding is somewhat skewed, so let's say this one has 30, this one has 31, this one has 29, the percentage difference is minimal. So, you know, performance-wise, it's still close enough to equally distributed that we don't care anymore. And this is to do with deciding a sufficiently large sharding amount for your database. But the flip side is, you don't want to go completely nuts. So let's say each one of my nodes suddenly has 10,000 partitions. Then the chances are I'm spinning up so many processes to look after each of those partitions, my node may fall over before I actually get up to the right number. So you need to think where you plan to scale to and how you plan to scale out in advance of designing your distributed system. Another one that you need to think about is fault tolerance. So here we have a nice friendly cluster. We have a 5-year cluster, which is very standard. We recommend this number for production if you're using OpenReact, or more, of course, not less, or any more. And so everything has roughly 60 to 50 to 60% CPU usage. It's ticking over nicely. It's all great. Now, let's say one of our servers decides to explode in a fireball of logic. And we've lost that server, it's gone down. You know, this happens, life happens, hardware dies. Or if you're using something like AWS and you have ephemeral storage, somebody turns it off, whoops. So, all the other nodes take over. Roughly, if you take the percentage for that, you add it to the others, it works out like this. Everybody's happy again. We're still running our system, everything's good. And by this point in time, usually your tech support staff will have noticed something and said, hey, we need to do something about this. So, what they do is, well, send in their highly trained engineer and say, server 4 has a problem, take it out of the rack, fix it, put it back in afterwards. And the engineer goes, yes, and they promptly unplug the wrong server. Anybody here has done that before? Really? Wow, you guys are good. Or you don't touch hardware, one or the other. Well done, everybody. Yes. Okay, well, I've done that before. It's embarrassing and it happens. So yes, so they unplugged the wrong server, which means, oh, whoops, but we're still live. The load from that one is then transferred to the others, and everything keeps ticking over. This is how a fault-tolerant distributed system should work. So, yay. To see this in action, this is a standard one. We took a cluster of React nodes, we took one offline, we waited for a bit, we turned it back on again, and this is what happens. So we see we killed the node here. The red one is the React cluster, by the way. The blue one is a control cluster, which is another React cluster that did nothing. It just kept running as normal. And this is, bear in mind, we're banging the updates through this. You know, this is how many million updates we're throwing through this cluster at the point in time. And how many transactions per second that are happening on the left. So we killed the node, and there's a huge drop in functionality. All the other nodes go, oh, one of the nodes has gone down. What do we do? I don't know, well, spin up virtual partitions to cover for the ones we just lost out of the entire system, and we'll take over nodes. So we have the initial one where we're busy doing partitions. We then have the partitions are all done, so the cluster takes over as normal. We start the node. There's a slight dip as they then say, oh, we have to give you all your data back so you know what the changes are. The node then comes fully back online, and we're looking good. In the next example, we do a slightly more aggressive one. So we kill the node, same as a minute ago. But then we wait for a second and we nuke the data. So maybe we wipe the disk that holds the data, or for it's Amazon, you use ephemeral storage and we turn off the node instead of restarting it. Oops, been there, done that. And your data is all gone. Oh dear, what do we do? Well, essentially OpenReact handles that as well. So your node is restarted and it comes up and says, hey, I'm back. And oh, I have no data. Whoops. What do we do now? So the other nodes again come through, they say, here's your data back, and it will copy across all the virtual partitions it's had until the node is able to fully repopulate itself. And then once it's repopulated, recover complete, and we're back to normal for performance, which is still kind of sweet. This is all fully automated. Let's see it. Yeah, this is a horrible graph, I know, sorry. But if we look at this one here shows the same example we saw a second ago. So we zoomed in on the time where we actually killed the node and killed its storage. So we see how the yellow node is the one we decided to attack. So the yellow node goes down, and then we put power in and it comes back up for a second. It says hello. And this basically shows how the purple node and the brown node, remember earlier I said that we have 3 copies of the data everywhere. So the purple node and the brown node have the other 2 copies. And the yellow node went offline, so stuck there. So they have to take over queries for that. The flip side of this is that once they start doing queries, you'll notice how the amount of load they handle comes back up until everything's back to normal at the end. And the title for this, which I should point out, is this total queries served. And there's a reason why it's different. Within OpenReact, as I said earlier, let's say you write to this node. And I've just touched the screen. I hate touch screens. What have I done? That's it. Okay. So you write to this node, and then it will say, oh, I've got new data. I shall tell the other 2 nodes that talk to me about it, and it shares the data with those. So we've got both the external queries, which goes to the client or the application or whatever you want to call it, and we have the internal queries that go between the nodes. And if we now look at what happens at the same time here with user-facing queries. So user-facing queries are the queries that go out to the outside world, whereas the queries we saw a second ago were the total number of queries served, which, as you saw, was slightly different. And this is where it becomes interesting. So within OpenReact, we have a feature where essentially we have an auction, where a new piece of work comes in, or a new query comes in, and nodes say, hey, I see that. Who can take this? And this is one done by availability. So a node that's not doing much will go, hey, I'll have that, and it grabs it very quickly. Whereas a node that's very busy, for example, nodes that help restoring another node, say, I'm kind of busy here, but I'd like to get, no, I missed it. I got that one. So you end up with your least busy nodes serving the majority of the queries, and your busiest nodes serving the minimal number of queries to make sure that overall performance is affected as little as possible. Which is why we see how the purple node and the brown node, suddenly the amount of user queries they serve drops like a stone. And as soon as the yellow node starts to come on, it pops up and goes, hi, I'm here, I have nothing. And the second later, oh, I've got a tiny bit of data. If there's a question on this data, I can serve it for you. For everything, I don't know. And the way that queries work in OpenReact is it comes in and it hits node number 1. Well, any generic node really. And the nodes all contain a shared ring. So every node knows where all the data is. So your query will come in and it'll say, yes, I've got that, here you are, or I don't have that, but I know a node that does. And it passes your query internally to another node, which will then retrieve the data, pass it back, and that'll pass it back to you. So even the slowest queries in OpenReact only hit 2 nodes before they come back to you. And that's what's happening here. So as soon as the yellow node is starting to come back online, it's happy to serve whatever little data it has. As it gets more and more data and the restoration is completed, then it goes back to serving a standard amount compared to everything else. If you put one on top of the other, you can see how the 2 of them phase over that period. Yeah, one other thing I should probably show you very briefly is a node replacement. So of course, we talked about hardware, and occasionally hardware gets old. I've decided I want to replace my old boxes with new boxes. So rather than taking my system down for a maintenance window and making all my customers unhappy, I can actually do this live in OpenReact. So I say, well, this is my old box, and this is my new box, and I'm going to say to you, I'm going to take you out, I'm going to replace you with this one, take all the partitions from that one. And that's exactly what we do. So we start the node replacement. So the old node, so we had node 4 die earlier, let's say, well, node 4 is clearly not reliable. We're going to replace it with a new node, which we'll call node 6. So then node 4 hands off all the partitions to node 6, everything comes back, and we're good to go again. And again, if we're just going to add a new node, we're going to scale up horizontally. So same kind of process here. We add a new node, we have a small drop in productivity of all the nodes saying, well, we need to reshuffle all the partitions between ourselves and give them to someone to the new node. So the reshuffle happens, there's a slight dip in performance, but as soon as that's completed, they start handing data off, everything becomes much faster and more efficient. Right, other features I should probably mention quickly, active anti-entropy. Who here has heard of things like bit rot? Okay, right. Let's cover that first. So bit rot is a fascinating process where, especially on magnetic media, it can happen in other media as well. Basically, data that was stored a long time ago, as you know, when things are stored to disk, they're stored in binary ones or zeros. So that's done with charge. You charge it, so it's charged up to a 1. And then when your disk is ready, it goes, well, that's above the charge level, so it's a 1. And that's below the charge level, so it's a 0. And the thing is that because it's charged, what does charge do over time? Joys of entropy?
Discharge.
Yes, it slowly discharges over time. It takes a really long time, but it happens. So if you have, I don't know, let's say, for example, you store a 4 terabyte backup file and you stick it in somewhere like OpenReact. And because it's a zip file, you have one bit go bad and the whole thing's lost. So you store it in here and you put it there and it's great. And then 7 years later, the auditors come in and say, we'd like to see that file, please. Oh, that's in the backup. So I'll go and and this is the hard way to learn about bit rot. So what OpenReact does is it has a system called active anti-entropy. Well, what that does is it goes over and it constantly reads the data in your database in the background. It doesn't spy on you, it just says, what is this, does this match that? So actually it will compare the differences. So let's say that we're using our example of 3 nodes again. So this one says, hey, this one should be this. And this one says, yeah, I agree, that should be that. And this one goes, what are you talking about? It's this. And the OpenReact will say, well, these two agree, and this one does not agree. Well, therefore, the chances are that these two can't be corrupted the same way. So probably these two are right, this one's wrong. So it will then overwrite the one that's wrong with a value from the two that are correct. Which means that even if you get bit rot on one disk, then it will come through and go, hang on, that's different, we're going to fix that. And because it's a fresh write, then it's being pushed back up to the correct charge. Theoretically, whether it's actually the same bit with the same charge, I don't know, but it rewrites its disk. So it's possible it's the exact same one, but in reality, it may not be. But either way, it goes through and it goes through, yes, determines the correct version, writes it out to all nodes.
Sorry.
Shoot.
So what happens if the 3 don't agree?
If all 3 don't agree, then you should probably manage your hardware better.
So it raises some kind of a user error. Or
Yes, so one that will generally, in a case like that, OpenReact, it will not see that as a sibling. Generally, you will receive an error for that if you want to get a. Okay, oh well, you're going to have to go into a bit of theory here. Okay, so there are different ways you can query OpenReact. So the standard way you query is you throw a query at it, and whichever node replies first is taken as your correct answer because anti-entropy should fix everything for you. Therefore, it should be correct no matter which node you hit. However, if you want to do a guaranteed everything is the same query, then you can say, I want to query maybe 2 or 3 primary nodes, this value, to make sure that they're all the same. And when it comes back, if there's a difference, then that's where we'll run into the same problem and it will probably flag it as an error. So in that case, if your hardware is falling to pieces, that might be the case and you will start to run into errors, but hopefully you should fix your hardware before you get to that level. Other stuff I should probably mention, yes. So as we talked earlier, OpenReact does not just make a cluster out of a couple of nodes. It will also allow replication between multiple clusters. So that can be unidirectional, where I am a read-write cluster, and the cluster over there is a read-only cluster. So this one does all the processing and stuff, and it's got big fancy machines, and this one's read-only, so we give it tiny machines because it's read-only, it doesn't need to do any processing. And then this cluster says, hey, I have new data for you, the other one says, thank you very much, I'll show that. We also have bidirectional, which means we can do things such as a live. You write to that one, it then shares the data with this one, you write to this one, it shares the data with that one, and everything works great. You can also do multi-direction as well, depending on how crazy you're feeling. There's a lot of flexibility within this. You can also do things that have different queries can sync different data. I'll cover this more later, but an example, everybody here familiar with GDPR? Do well on the Okay, right, data privacy. So in the European Union, there's a law which is basically called GDPR. And what it says is that personal data about European citizens cannot be stored anywhere outside of Europe, which can make life difficult. So let's say I'm a big US company and I have this awesome system and you have many, many users. And I also have customers in Europe and I can't store any data about them. I don't know who they are anymore. Well, that's going to be a problem. So, before this law was in place, you'd have a cluster in America, a cluster in somewhere in Europe, and they'd share data with each other, and everything would be wonderful, and everyone was happy. When GDPR kicked in, then you run into the problem that the data in Europe is not allowed to leave Europe, but you still want to share as much data as possible. So what you can do is you can build a specific queue within OpenReact to say this data should be copied to the US, and this one should not. Which essentially means that from the application developer's point of view, all they need to do is say, well, yeah, that's European data, so stick your GDPR bucket. It's not actually called the GDPR bucket, you can call it whatever you want, but basically stick it in a bucket that replicates on this queue or does not. And that means all your US data you can then sync to Europe, but the European data, you can only sync the safe stuff to the US. And that all happens automatically in the background. So that's one of the advantages with different queues. As well as this, we can also do things such as to do all the replication. We have a reconciliation engine, and you can also connect external things to it. For example, OpenSearch. Quick check if we know OpenSearch. One. Very briefly, what does OpenSearch do?
It's the open source version of Elasticsearch.
Yes, that's good enough for me. Thank you. Right, so one of the things that you'll run into a problem with React is OpenReact is limited on things like fuzzy searches. Find me a city with a letter O in it. That's really, really hard to do in NoSQL because it's not designed to cover with stuff like that. NoSQL works really well with direct queries. For example, get me a list of cities within Japan. Easy, I can do that because I have a list that has all the cities in the world and these are tagged with Japan. So I just find Japan and it says, hey, here are your cities, go. But if I want to do a flat one, I have no idea how to do that. It just doesn't work. We can't do the equivalent of SQL star O star. Doesn't work in Rome. No, bad, do not do that. But if you connect an external engine like OpenSearch, suddenly we can. So what we do is we use the power of OpenSearch's indexes to index everything in React. But to be perfectly honest, OpenReact scales really, really, really well compared to OpenSearch. So you have a huge database I won't say you can't search, you can't do fluffy searches with, and you have this incredibly powerful search engine that doesn't scale to incredible scale that well. So we take the search bit from this, which is awesome, and we take the scaling bit from that, we plug them together, and you've got a really fine system. Right, moving on, system architecture, and this is where I have an example of an absolutely nuts setup you can do with OpenReact to give you an idea of the possibilities available to you. So we're going to start off, we're going to say that's us, we are a client or an application or whatever you want to call it, something that talks to OpenReact. And we're going to say, well, we're going to have one main cluster and another main cluster and they can replicate between each other. Everybody good so far? Well, I forgot where I am, so I think we need labels. Right. So we're going to extend this, and not only are we like that, we are a company that has a whole bunch of labs that run mini clusters within themselves, and they need to share some data with each other, but not everything. So here's a bunch of labs. I am really this nuts. So let's stick them out. So first of all, we take our user, we set up 2 central clusters, and we stick labs, and this is, call it geolocation. These ones are near that one, so they may as well talk to that one. Those ones near the other one, may as well talk to that one. And we set up replication. Central A talks to Central B talks back to Central A, they share data between them, so whichever one you talk to, everybody has the same data. Yeah. From there, we then add replication in a similar way between each lab. This can be unidirectional or bidirectional, but labs, they want, let's say this lab here, because I can reach it. This lab here doesn't need to know all the data in this lab. In fact, chances are they do research on completely different things and have no interest whatsoever in each other's data. But maybe this lab here and this lab here, this one might do the research first, and then the results of that are actually fed into the tests run in this lab. That's actually perfectly reasonable. So in these cases, maybe it should be bidirectional, where the data from this one is syncs up to here, syncs through there, and syncs down to there. Or it could just be unidirectional, where I don't need any data for anywhere else, so I'm just going to dump straight into here, and that's it, I'm finished. But the two main ones know about everything at all the different points in time, and the user can quite happily talk to central A or central B, or we could even have a load balancer up, so it would just be completely random on which one we talk to in the classic one there. And because everything on one side can talk to everything on the other side, then everybody's happy no matter what happens, and short of a complete network loss, which in this case would probably involve the entire internet going down, we would expect it to continue working all the time. And we actually see customers run clusters not quite this complicated, but we do see ones where you'll do things such as you'll have maybe one cluster in West Coast, one cluster in mid US, and one cluster in the East Coast, or you have people with one in the US, one in Europe, and one in Asia, to make sure that it's always have something up, and even if one cluster in a country goes down, you just point it at the other ones and it still works. It's just a tiny bit slower. And that's network lag, nothing to do with OpenReact. So when should you use it? People who use it, financial institutions. Believe it or not, they do. One of our largest customers is a financial institution, it's a bank. Every single transaction the bank runs goes through OpenReact. So it's definitely stable and reliable enough. I admit they copy a lot more numbers of, they don't have 3 copies, they have a lot more copies. But essentially, yes, it's very usable. Government organizations, I know of a National Health Service that does this. E-commerce, one of our customers is Japan's second biggest online retailer. Manufacturing, one of China's major electronics manufacturers runs on OpenReact. Messaging, people may not be aware of this. Apple used to run iMessage on React back in the day. Line, which is the most popular messaging tool in Japan, runs on OpenReact. IoT, there's another obvious one. If you've got 10 million devices all around the planet, having a central reliable database where they can throw stuff at any time, hit any node, and it still works, is a very useful way to store stuff. Especially if you're doing hundreds, if not thousands, of transactions every single day. So, usage advantages. OpenReact runs on cloud or commodity hardware. How commodity are we talking here? In Japan, I have to file taxes on cryptocurrency. That means for every single transaction I make, I have to register it with the Japanese tax office saying how much was the transaction for, what point in time did it happen, and what was the equivalent in Japanese yen at that point in time, which is an absolute nightmare. So I wrote myself a piece of software to do this, and what I do is I basically grab data about all the different cryptocurrencies in the world. I grab details about all different exchange rates in the world, and I stick it in an OpenReact cluster that runs on Raspberry Pis. So I have 5 Raspberry Pis with USB 4 terabyte drives, and it just ticks over. I mean, to be fair, it went down once, but it went down because I unplugged it to move house. But other than that, I've had 100% uptime for 7 years now, which that's pretty good in my opinion. But yes, people often run it in slightly bigger boxes. I run a copy on this laptop for when I'm doing test work. It will run as a single node, but please only do that for development work. Otherwise, bad things can happen in production. Lose your node, you lose everything. It's horizontally and vertically scalable. Add more boxes or just have bigger boxes. It's fault tolerant and eventually consistent. Does everybody know what I mean by eventually consistent?
Yeah. There might be some difference in data between 2 clusters, but eventually they'll come to the same.
Yes. Essentially, this relates back to CAP theorem. Everybody familiar with CAP theorem? Okay. So CAP theorem is an absolutely fascinating idea where you have consistency, availability, and network partition. CAMP is just, no, let's not go there. So the key C part is consistency, which means that if I talk to this node, or this node, will it give me the same response? Availability is, are all nodes available at the same time? And network partition is, will it continue to work if there is a network partition? And of course, the challenge with CAP theorem is it's meant to be theoretically impossible to have all 3 at the same time. If I write something to this node here, I can't guarantee it will be straight away at these nodes. If I do guarantee all nodes will give the same response, one of my hardware things died. My system's no longer fully available. It's one of these, but the best you can do too. So OpenReact is designed in a way where we do accessibility and functioning in a network partition. That's what we do out of the box, which is why we have to be eventually consistent, which is exactly as you said. You wait for a bit and then it will come back together and everybody will have the same. Right. And also, as we talked about a second ago, we have geo-redundancy. You can build a cluster here in US or another one in Asia and do things like that. And one of the other reasons that people use OpenReact is GDPR and Cloud Act avoidance. We talked about GDPR a second ago. Anybody know the Cloud Act? No? Okay. This is a fascinating piece of US legislation. So in 2016, America decided that they can talk to a cloud provider, Amazon, Azure, Google, whoever, and say, hey, we'd like to have all your data on this place. Which, that's kind of common in America. It's the kind of thing you expect. Anybody will give everything to the American government because they're Americans and it's very patriotic. Woohoo, great, okay, I have no problems with that. The problem comes when the Cloud Act specifies that the American government can talk to any American company and ask them to give any data they have on any client anywhere to the American government, and they don't have to tell the client that the data was given. That suddenly becomes a lot more interesting, doesn't it? And a classic example, so what was it? A few years ago, there was data stored on an iPhone that was held in a data center in Ireland. So Apple said, we're not going to give you this because it's in Ireland. And that's not right. In the US, we can give you the data, but that's under Ireland, so we can't. And there was a huge legal trial and stuff about this. Cloud Act gets around that. American government can now say to them, well, hey, Apple, I want this data. Fetch. And Apple will say, well, we really don't want to give you that, but you kind of got our hands tied. Yeah, okay, here you are. And this is why you may want to use something like OpenReact. If you run it on Amazon or let's say you use an online cloud service, for example, DynamoDB. If your data's in there, then Amazon can say to you, hey, DynamoDB user, US government wants your data. And that can be even if you're a European company or an Asian company. If you use DynamoDB, then anytime the US government can steal your database. Well, steal is probably not the right word. Copy your data and do research on it. For whatever legal reason they justify at the time. Whereas if you run it on your own hardware, that's not going to happen unless you're in the US, in which case you're legally required to do that anyway. So that's your choice. Anyway, that's Cloud Act, and that's one of the reasons why you might want to consider not using services that are liable to be hit by that. Which is why hyperscalers are actually surprisingly dangerous in this day and age, assuming you want to make sure your data for your people are private. And of course, another way to do that is OpenReact can run in an air-gapped environment. How do you stop your boxes being hacked from somebody on the internet? Well, you unplug the internet. That's surprisingly hard to get through. And that's the other thing that's unique about something at the scale of React is, let's see DynamoDB do that, and the internet has gone down and my database has gone away because it's somewhere in Amazon and I can't reach the internet. Whereas this one here, well, it's just a box there, it works fine. Right, so why is OpenReact insecure out of the box? There's actually a very good reason for that. It's easy to set up, assuming you're not afraid of the command line, which some people are these days. Basically, how do you set up OpenReact? Well, I download the binary, I install it, and I say start. And that's it. I suddenly have OpenReact running. I mean, to do everything else, clustering and setting up your data and how you want to structure it, that's a bit more complicated. But the basics are download, install, start, and go. Everything's good. And that's why it's insecure out of the box. If you wanted to do a fully secure version of a fully secure version of OpenReact, that takes a bit more work. And if you get it wrong, then suddenly you lose access to everything until you undo whatever mistake you made a minute ago. So, what factors are there within OpenReact that apply to your security? First of all, I'll explain these all in a second. We have EPMD, which is the Erlang port map daemon. We have HTTP queries, which sounds innocuous enough. And we have user permissions. I'm going to go through and explain why this is an issue and what we can do about that. So just a second. There you go. So EPMD is the Erlang port map daemon. Does anybody know what this does? Anybody here know Erlang, by the way? Programming language. No one? No. Wow. It's a great language. Look it up. Erlang is originally used for telecom protocols. It's a ridiculously stable distributed system. I mean, to give you an example how stable it is, when was the last time you had a phone call crash on you? Precisely. This was developed in the 1970s to run essentially switchboards, and then it became more and more advanced. But the same basic distributed stability has been there for years and years and years and years, which is why things that are run on Erlang, they're not designed to crash, they're designed to fail and recover, which is very different to how much modern software is. It works, and it fell over. We have to do a full stack trace to find out. In Erlang, it fell over, but it restarted itself and it continued. Which is why you don't have phone calls crash on you. If something's going to crash on you, it's going to be your smartphone or the application running something or something else crashed or whatever. The chances are the actual phone call itself will not crash at all. So, what EPMD does within Erlang is, as Erlang is a distributed system, I need to be able to know what everybody else in my cluster does, because I know nothing. It's a bit like, we have a great bunch of people come to listen to my talk and I know almost nothing about any of you. Sorry, but it's true. And probably you don't know that much about me either, which is fair, but still weird. So, what does it do? Basically, it tells other nodes about what's available. So if you come and talk to me, I'd say, hey, I'm an EPMD. And these are all the ports available on my Erlang box. Please feel free to come and talk to me when you want to. And that's what EPMD does. It's a required function for React to run. It's a distributed basis. We have database, we have to talk to the other nodes. That's life. It communicates with a shared cookie. So, it's not completely unsecure. If you know the magic word, I will tell you all my ports. If you don't know the magic word, I will not. And the problem with OpenReact is the default cookie for over 17 years now is React, and that's published all over the internet. So if I come into a default stand-up version of React and I say, hey, are you React? Because yes, I am. Here are my followers. And that's horribly insecure. So yes, why is EPMD a risk? So let's say a malicious third party gains control of the cookie. What will that incur? Well, first of all, the malicious third party can then communicate with other nodes within your React cluster. You get full node discovery, as it not able to tell you about the other nodes, it will tell you what ports available, they know everything. But of course, once they have access to the cookie, a slightly more advanced person will actually be able to use that to attack an OpenReact node and overwrite low priority functions. Which of course means they can inject malicious code. But not only can they do that, they can also issue malicious Erlang commands. So not only can they take down the database from inside, but Erlang allows you to execute system level stuff as well. So they can then issue malicious OS level commands, do everything from phone home to install rootkit to whatever. That's kind of bad, really, isn't it? Let's talk about HTTP queries. So, OpenReact listens for HTTP requests by default. Initially, actually acts as two interfaces. One is HTTP, the other one's protocol buffers. Binary versus standard. And they're both available by default. So, anybody see a problem here? HTTP supports create, read, update, and delete. Standard API, you'd expect CRUD operations, yeah? Anybody see where we're going with this yet?
Send malicious requests.
Oh, well, no. First of all, it's HTTP. It's not HTTPS. Yes, your requests are not encrypted, which means third parties can read the data on the wire. Anybody here use Wireshark TCP dump? Yep. Basically, it's a packet sniffer. You can sniff network traffic and read what's going on inside it. So yeah, this is a great way to practice that if you want to. But not only to do that, third parties can issue curl requests to the data, including updates and deletes. So exactly as you said a second ago, people can then issue malicious requests and affect your data. Everybody here curl familiar? Yes? Yes, yes. Okay, good. wget will work as well if you're interested, although you can't write with wget, I think. Of course, because people can then access your data, that will allow for potential data leaks, obviously, and also potential ransom attacks. I come in, I have the ability to upload your data, I read your data, I encrypt it with my key, I save it back to your database, and because your database has over 10 billion keys, you didn't notice for the first 5 million I did. And of course, there's user permissions as well, which is another issue. So, by default, OpenReact has one user for everyone. Yay, nice and easy, simple, straight work out of the box. But of course, that means anybody can read anybody else's data, which means anybody can update or delete any data. You see where we're going with this already, don't you? Which allows for potential data leaks and again for potential ransom attacks. So these are out-the-box problems you encounter with OpenReact with a default setup. What can we do about them? So default remedies. So well, EPMD, it's a shared cookie everybody knows, so change a cookie. If my password is no longer Open Sesame, it's something else, then nobody knows what it is. So yes, security by obscurity, technically that's true, but it needs to be there for the nodes to work together. And if you have a cookie that's maybe 64 characters long, by the time someone's brute forced that, you should probably have noticed if you've got people running decent network security on your system. HTTP, well, install an SSL, and it's HTTPS. Yeah, that's a bit of self one. So on the plus side, that does secure the connection so people can't listen, but it also means that they can still do direct reads and writes, just their direct reads and writes are now secure. And finally, user permissions. So React has a whole suite of things inside it called React Security. And what this allows you to do is essentially not only enable user permissions, and you create users, they can be user password, you can do it by IP address, you can do it by talking to, for example, some kind of database to get your users. You set it up many different ways, but essentially you can prevent access without a valid user. And other things you can do with it, which is also kind of cool, is you can say, for example, these buckets, any user can use it, but they're read-only. Whereas this user is allowed to write to that bucket because they're special. So you can do very granular security settings, although that does take a while to get the hang of. But why is that still not enough? I mean, we've secured the requests, people can't guess our cookie anymore because it's obscenely long, connections are secure, and user can't log in. Why? Well, users can, of course, log in, non-users can't log in. Why is that not enough? What have we missed? We secured everything. So connections to OpenReact are now encrypted. I come in via the HTTP API or the protocol buffers, as that's already done for us, and it's encrypted. Yay! And of course, we require valid credentials to talk. So yeah, that's kind of good. I need a username, a password, and an encrypted connection. You know, that sounds pretty secure to me. But as we talked about earlier, OpenReact is a distributed database. What do distributed databases need to do?
Distribute data. Exactly.
They need to sync the data between the nodes, and the Erlang connections between the nodes are not encrypted. So people can't listen on the wire for the user queries, which is sad because those are the really easy ones to get into. But if you listen to the data traffic between the nodes, you can actually work out what's going on and theoretically steal data from there. That's a whole level harder to do, but it's still doable. What else do we have issues with? Well, OpenReact runs on open regular Linux servers. Don't do all that, it doesn't matter. OpenReact runs a large code base with many ports in use. Anybody see where we're going? I got a feeling we do, yes. So in IT, new attack vectors are being discovered daily. Zero-day exploits happen, even in our latest release, which is actually 2 days ago, although we haven't finished the packages yet, so you'll see that next couple of days. But third parties may try to access the server ports directly. Maybe they found a new hack, maybe they found something else, we don't know. And we can't really secure against stuff we don't know about because it's hard. Right. And what else do we have? So, another classic one with OpenReact. With OpenReact, like pretty much every other database in the world, we need storage. We need to keep your data somewhere. Many companies run OpenReact on their own hardware. Can we see where we're going? Physical hardware can be stolen. What's on this server? I don't know. Let's take it home and find out. And that's the issue. So yes, even without the Open React usernames and passwords we set up a minute ago, if you steal the storage device, you can read exactly what's going on inside it. So how do we deal with these harder issues that we've just encountered? I mean, we've locked down the database itself, but there are still vulnerabilities we didn't cover. So what else can we do? Well, secure even more. Connections between nodes are not encrypted. Any solutions?
Encrypted.
Bingo! We encrypt them. So for the moment, point-to-point VPNs or tunnels. That will work nicely. Third parties are accessing my server ports directly. Solution?
Only allow. You don't allow inbound traffic or something. Or allow rules.
Yes, there we go. Firewall rules. Turn on the firewall. Say yes to you, but no to you. So you're naughty. Don't trust you. Physical hardware can be stolen. What can we do about that?
Sharing responsibility.
Better security.
Bit more specific. Both of those are true, but yes, how do you make it more specific? Thank you. Yes, we encrypt your OS or your data. Awesome. So yes, that's essentially how we secure it, and everybody knew that. Why are you here? Go on, that's the main part of the talk. But let's talk about that in more detail. So tunnels or VPNs. Incidentally, OpenReact runs on OTP 28. That's the version of Erlang for those not familiar. No, we don't run on 28. I apologize. Currently, the live version runs on 24. 3.4 will be released in late autumn this year. That will run on OTP 26. Unfortunately, encryption for free between nodes doesn't happen until OTP 28. So you'll probably have to wait for version 4.0, which will be next year, I expect. So, we have a solution in the works, we're just not there yet because the programming language we run on doesn't support that yet. But we will be there. In the meantime, you can use open source applications such as Tink. Anybody familiar with that? Okay, it's a standard Linux tool. You should be able to get that with your local distribution at install Tink or DNF install Tink or whatever your zipper, whatever your local package manager is. That should probably be able to get you Tink straight away. It's very simple setup. I'll be perfectly honest, it's not the most secure tool out there, but it's better than nothing. From there, another one you can do, which is also free with most people's distribution, is StrongSwap. And that gives you, it's harder to set up, but it gives you IPsec between nodes. In this case, in these cases, what you want to do is you have to set up your tunnels first, and then install OpenReact and cluster it afterwards, which is a bit of a pain to do retroactively, as you need to redo a whole bunch of stuff, which is an absolute nightmare. But if you're doing it in advance and thinking about your system, then this is the way to do about it in production. Of course, firewall restrictions. So we're talking about open source tools. Well, you're probably running this on Linux, which is open source most of the time. You might be a Red Hat person, but your Linux install should have a firewall. So use your firewall, basically. Third-party firewalls are also available. You can pay for these, or you can use software ones, hardware ones. There's all kinds of wonderful stuff out there if you're looking for it. As mentioned earlier, we should restrict the firewall to known IPs and relevant ports only. For example, application there needs only the API. It does not need access to EPMD. One of the classic strategies I've seen employed in some large organizations, make sure that everything can talk to everything else within the organization. Great, but if my application layer suddenly knows where all my ports are in Erlang and somebody hacks the application layer, am I happy with that? No, not really. And last one, encrypting your data. So encryption at rest is the classic one people talk about. There are two ways to go about this. You can encrypt your data directly via the application. So my application runs the data, it encrypts it, and then it stores it in OpenReact in an encrypted form. Plus side, that's more secure because if somebody runs off with your OpenReact server, even if they started up, the data is still encrypted. And as the keys are in your application layer, they can't access your data because it's all encrypted. Huzzah! The problem with that is, if you're trying to do something like a range search, for example, find me all data between 2010 and 2020, I can't do that because my metadata is encrypted, so I don't know what it is. That gives you then two compromises. You can either choose to store your data in a non-encrypted form, which if somebody's stolen your data means they can do a targeted search to find which data they need to crack the encryption for, or you can encrypt it and give up on that functionality. That's a bit of a trade-off. Choose the lesser of two evils for what you're building. On the plus side, metadata that's one-to-one matching, for example, find me all the cities named in all the cities in Japan. Well, Japan will just encrypt that and put it in the search, and because that's the metadata encrypted will match the metadata encrypted. That will match, so that will still work. And it brings me back to encrypted data, and I just decrypt it, and there's my list of cities. So yes, oh yeah, will impact free search. True. Other way to do about it is encrypt your disks. For example, file system encryption. I think ZFS is a popular one now that allows you to encrypt it. But that does have a minor problem of if they access your box while it's running, decryption is automatic. Yep, if they hack your box while it's running, decryption is automatic. So yeah, you have to choose again lesser of two evils there. On the plus side, you still get your full search functionality if you have disk-based encryption. But then again, if it's stolen or they access it while you're live, you're in trouble. So I seem to have gone through today's talk slightly faster today. So let's follow the logic. What actually happens in this process? And this process, which is what I apply to not just OpenReact, but to applications in general, here's an insecure application. This could be anything. It could be a web server, it could be a mobile app, it could be anything you want, we don't mind. So what should we do about it? Well, let's go check it out. Does it have any security tools we can use? Some do, like OpenReact. Yay! So yes, use the tools. So we'll change out our cookie and we'll add SSLs and we'll create users and we're kind of safe. But are we fully secure now? No, certainly not. Okay, so what do we do next? Well, let's try and identify and fix the areas using third-party tools as we talked about. We can use IPsec connections, or we just use tunnels or whatever. We can encrypt our file system or whatever we choose to do. So now let's have a look at that in further detail. Is the OS fully secure as well? And that's part of where we use the extra tools. So we identify and fix insecure OS areas, which is, yeah, file system encryption is technically an OS area as well, which probably needs to be fixed on both sides. Firewalls, again, that's more OS side as well, but can also be application level. So that takes us through. So test, and I cannot emphasize this enough. Test it yourself. Ask your mate to test it. Pay a penetration tester to break into it for you if you've got the budget. Seriously, test your stuff. It costs you a lot to test, but it costs you a lot less than having your system go down or having your data stolen. Is it secure now? No. Do it again. So we run through our entire process. Are we secure now? We're back. We have our insecure application. What else can we do? Is it secure now? Well, yes. Really? Let's do it again. And this is what I mean. We need to keep doing it. Security is always a PDCA cycle. Even if you fix it once, you'll need to come back and fix it again and again and again, because no matter how well or how secure your system may be, chances are somebody's trying to break into a similar piece of software running similar code soon, which will be made publicly available on the dark web, and they'll use it against you in future. So yes, it's a constant stinky pattern we have to fight because there are nasty people in the world, and I really wish there weren't because things would be so much nicer. But anyway, assuming you do make it secure, yes, and we finally finished, woohoo! And this process should actually be your standard software process testing for security on anything you use. So I've actually come through this a lot faster than I expected. So let's do a quick wrap up with Q&A. So today I gave you a quick introduction to TI Tokyo, saying why am I talking to you? I believe I know something about OpenReact, and I believe I know a little bit about training, but you may have other opinions. We talked about what is OpenReact and why, when we should use it. Also, why is pretty cool, but when, yes, it has some great applications. Do not use it as a replacement for your SQL database unless you plan to seriously rewrite your application. I will say that. We talked about potential threats, different ways people will come and attack you, or things are at least open too much. So we talked about using built-in tools and tuning on how to get by those. We also talked about using external tools, and it's surprisingly simple. mean, given how complicated this database is, what did we actually do? Well, external tools, well, we secured the file system by encrypting it, and we added tunnels. That wasn't hard, was it? But simple stuff like this, people miss out on. I mean, the number of times I've worked with production systems for major clients, and they've, what? One of Japan's biggest data companies, which everybody in this room will have heard of, but I believe I'm not allowed to name despite the fact they're a customer, they run a full desktop environment on their OpenReact servers. I don't just mean full desktop environment as in here's a screen. I mean as in it has everything from a development suite to audio codecs. That's the kind of level of wow. And it's really shocking how much people do this. It seems to be really odd, but from people I've worked with and talked to, the larger the organization, the less thought goes into IT. It's as if, you know, here's a $5 million project, and we outsourced it to this company, who outsourced it to this company, who outsourced it to this company, and every single layer took a margin. And there's just one small board sitting somewhere who actually wrote this huge application for this company, and they use it. And you look at the source code, and it's a piece of rubbish. And that's how things seem to be in the world these days. People need to think about things in more detail and do it properly. I mean, don't get me wrong, some companies do absolutely awesome stuff and full respect to them. But lots of the ones I've worked with are absolutely terrible. You occasionally get the, you know, the diamond in the rough. Wow, you guys are awesome. A bit like the bank we work with. They are awesome. They do really good stuff, and I'm most impressed. They give us challenging questions and go, "That's a great question. We'd love to answer that because we never thought of that. We'll find out for you." But yes, really get into looking at all the different options, and some of them are surprisingly simple and just aren't done for some reason. Anyway, that brings me to the end of our talk for today. We're slightly before time, but bear with me. If you would like to talk to me, that's me. If you'd like to get involved with OpenReact, come and check us out. Here's a whole bunch of stuff. Please feel free to take a photo of the slide if you need to, or not if you hate me. If you're wondering what the QR code is for, we're doing a sweepstake at the moment, and as you notice, our company character is Chio-chan. If I was an organized person who was reliable, I would have not left the doll on the desk at home, and instead would have brought it with me. So what I had to do is create an extra slide. This is Chio-chan, who you can win. You fill in the survey, there's a chance. About this big for reference. Yeah, all Japanese companies have to have a mascot, so that's ours. So, complete survey, you have a chance to win your own Chio-chan. They're very rare, there are only 10 in existence. So, yeah, collectible item. And yeah, that's about it, really. If anybody would like to ask any further questions, please feel free, open the floor. Ooh, one other thing before I forget, people may be wondering why, if you go to our website, we don't have Chio-chan anywhere. That's because our website's currently being redone. Assuming that Alton Tab is actually going to work with me, that's our new website, which does have Chio-chan lurking in here somewhere. There's, yeah, nice. Yes, she does lurk in. This is the draft for the new one. This is not live yet. So that's where she is, and she's not there now because we haven't got our website yet. Other than that, oh yes, I'm also going to talk to you about this. Today's one will finish here after, if you're, no. Yes, here we go. After today's talk, there will be an event apparently in YC Conservative and Newtown. These are directions. Go check it out. I'm afraid I need to run away and jump on a plane as I have a meeting tomorrow I need to attend in Tokyo. But yeah, there's a ridiculously long web page with arrows. This easy to remember link is at the top of the screen. Good luck! Other than that, yes, I'd say thank you very much. I'm Nick Sanders on behalf of TN Tokyo, and we have Yuyan, who's been great with all the audio visual stuff earlier, especially telling me that my mic is turned off. So thank you very much. Any questions?
Yeah.
Go for it, please.
Disk encryption and nodes talking to each other.
Yes.
Does OpenReact provide that as a configuration where you can decide that you want to write the data in an encrypted format?
All right. If you want to write an encrypted format, that's done at application level. So you tell your application, encrypt this data, and then you send the encrypted data to OpenReact.
So there's no configuration.
There's no fancy configuration at all there. OpenReact is incredibly flexible in that you can store anything. For example, let's say in OpenReact things are usually stored by buckets and keys. So let's say I have a bucket called user, or maybe even better username. So user ABCD. And then within that, you'd have, for example, first name, family name, date of birth, and avatar. And that will be text, JPEG, or text, PNG, or even a video. And it can store things quite happily like that, which gives you a lot of flexibility to do what you want. Of course, if you're going to encrypt those, you then have to write. You can choose whether or not you encrypt the names, but provided you're able to decrypt from the application side, then that's entirely up to you. So you could do encrypted username, encrypted family name, and then encrypted data, or you could actually have username ABCD, family name, and then just store the family name and encrypted data. That's entirely up to the user level.
And then you're also saying something about how if you already have an existing database that's running SQL, you wouldn't want to reuse port this over, migrate this over to OpenReact. What's the reason for that?
That's an interesting question. That's a bit double-sided. So long term, that's probably a genius move. Short term, it's absolute suicide. The reason for that is that SQL will use things such as joins and unions and all kinds of stuff to do huge queries. I mean, one of the biggest differences between SQL and NoSQL is SQL will allow you to do huge queries which process huge amounts of data and then give you one big result. NoSQL, on the other hand, will usually allow you to do blindingly fast queries, but you can't do complicated queries. Which means that you can't just, for example, in SQL, you can probably move from MariaDB to Postgres to Microsoft SQL Server. And you'll need to do a few tweaks to your code base, but it's not that hard. However, if you want to go from Postgres or whatever to OpenReact, you have to rewrite most of your code base because the queries will just be completely different. So if you want to do a join in something like OpenReact, what you would probably do is you do a secondary index query, and you do another secondary index query, and then you do a MapReduce, and then return the results from that. Or if it's a simple join, you just send a whole bunch of gets to OpenReact in parallel. I mean, that's the nice thing about it. The gets are in parallel. So if I chuck 1 million gets at OpenReact, it goes, yeah, okay, here you are. And because they're in parallel, every single get is as fast as the next one. Which means that instead of going get 1, get 2, get 3, which in SQL is a nightmare. If you do query A and then do query B and query C, it's going to take forever because the to the database, back from the database multiple times takes forever. Whereas in OpenReact, you do it in parallel. There you are straight away, and then you just process the application level in memory. But one of the interesting ones that I am starting to see is people using hybrid systems. So stuff that gets hit a lot in SQL, but doesn't actually need SQL's level of complexity. So let's say a user sign-in form. What do? Well, I set my bucket name as the username, for example, user ABCD, as we did a second ago. And as the key, we then have password hash, and then we store the hashed version of their password. Now in SQL, what you do is you go into your user table, which maybe have 10 million users, and then you do a lookup and you find the right user, and then you scroll across and you find the password, and then you take both of those back to the application and match them. In OpenReact, you just say get, thank you, I'm done. Because in that query where in SQL you need to do where username equals this and password hash equals that. In OpenReact, I just say, well, get me the hashed password for this user. And if I get a not found, it's not a valid user. And then once the password hash comes back, I then just compare that to the password hash I've hashed locally, and it's a valid password, let them in or don't let them in. So, simple functions like that, you can migrate from SQL to NoSQL really, really easily. Same level of update username, update password, that's really easy. Yes, basically it's just an update operation. You just need to change your query from SQL to NoSQL, and you're good to go. But very, very complicated queries that rely on joining multiple tables together, a classic one where you've got a 10-line SQL query, that is something you probably don't want to migrate to OpenReact without really, really rethinking how to do that query in a way that's, SQL is essentially it's Excel, isn't it? You've got a whole bunch of tables and you switch between the sheets because you're switching between tables. There you go. It's essentially, you can think of SQL as that. If you want to think of OpenReact or NoSQL, think of it as a file system. So, you have, well, if you're in Windows, I don't know, C, users, my user, my documents, and then my value or my file or whatever. That's essentially what you can do with NoSQL. And to try and switch from SQL tables to NoSQL bucket type storage takes a bit of a mind shift. I mean, to make it work well, if you store as you plan to query your data, then NoSQL is absolutely amazing and the speed will blow you away. However, if you go for the more SQL-y approach, well, if we just dump all the data in this logical table and then write a query that's because our data is stored in such a weird way that we have to join together 7 million tables to get the answer. That's not an OpenReact style, a NoSQL query you can do. That's just nuts. Well, if it's that many tables, that's clearly bad system design. But NoSQL, think very carefully about how you're going to query it. SQL, think how you want to store it so it's easy to query anything. Which is why one of the secrets to successful NoSQL usage is actually data duplication. You'll often see ones where, let's say you have a username and an email address. So you do a lookup of, you have bucket's name is user ABC and then key is email. But then you have another one that bucket name is email and username is ABCD. So our data is duplicated. So rather than having to trawl through all the usernames to find the email address, to work out which user ID that works to, instead I just look it up by by email address and I can get the user ID straight away. And that's another technical strategy to actually implement NoSQL in an effective way. It's just duplicate the data you want to query in multiple different ways to make so that when you read it, it's blindingly fast. Does that answer your question?
Yeah.
Cool.
So what about migrating from another NoSQL database to OpenReact?
Right, that depends on the query language used. This will be an ETS problem no matter how you look at it, where you'll have to extract it from the old database in the way they store it and then put it in OpenReact in the way that you store it. It's fully doable. I know of migration from Dynamo to OpenReact because they wanted greater performance. Yes, we can actually say that, isn't that cool? And I know the decision to go the other way because even though they knew they would lose performance and it cost more money, they didn't believe in open source software. They prefer to have somebody else they can blame. The system went down, it was our engineers' fault, sorry. They didn't think that was very good. Rather, well, it went down, but it's Amazon. And even if you try to blame Amazon, they say, yes, but there's a more expensive tier that you could have had and it wouldn't have gone down. And even when you're not, and you get right to the top, they say, well, actually, there's another one, it's just not published. But, if you can blame Amazon and Amazon say, well, it wasn't us, you just paid for a cheap one, then, it's nobody's fault and the press will let you get away with it. Whereas if your system goes down and it's your engineers, you tend to get blamed. So that's why people will sometimes move from OpenReact to a paid solution, simply because they want to be able to put the blame on someone else. Yes, exactly. Anything else? Okay, fair enough. I'm going to say thank you very much for all of you. If you're up to the events, please enjoy the evening. Yeah, thanks for coming. And I'm going to stop the recording here. Yes, no questions in the chat, which is good. And I shall close your video.